Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on Math Basic Course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside as we jump into the Chapter 3 review in the Big Ideas Math Integrated Math 3 textbook. This is all things polynomials. We have 9 sections to cover, 44 questions in total, with some general examples for each individual section to cover. And if you want to find a specific question, you can jump down to the description section down below. You can go to the timestamps where we find each question. You can click on that timestamp or touch it with if you're on your phone or a tablet or something like that. And you can also download this PDF as well as the graph paper PDF I'll provide, because we're going to have to do some graphs. You also probably want your graphing calculator out. Not just any old calculator, but a graphing calculator. Or if not, at least follow along with what I'm doing so you can make sense of it. Without further ado, let's go ahead and let's get started. We're going to begin with section 3.1 on graphing polynomial functions. At the time, we were specifically using a table, which is fair for these kinds of questions, and it helps us understand what it is these functions can look like as a whole. Now, polynomials are any monomials, I should say, but any sets of terms where the variables are raised to whole number exponents. So it doesn't have to be a cubic. It could be a quadratic or linear or constant. We could go as small as that, but we were doing those more in the other sections. Here we're really looking for cubic onward and what their overall behavior can be. And here's this cubic function graphed here. Now, how do we end up graphing it? Well, we're going to use a table. Now, they go from -3 to 3. In the sections, we were doing a lot of -2 to 2. Depends on how big or small the numbers get. In this case, these are reasonable, at least these ones right here. 3,35 looks a little out of reach, and we recognize that, and we'll probably not plot that point. But they're plotting these points here, -3, -1, -2, 0. I don't see where -1 is plotted, but I guess it's that one right there. And here's the y-intercept, 1, -9, and 2, 4. And we plot those points and draw the curve. Now, the understanding of this curve for us will be based on the degree of the polynomial. If it's an odd degree function, it has the ability to, as this one is, start down and finish up. Or start up and finish down, like that. Cubics, 5th power, 7th power, things like that. Even linear technically do that. They just don't curve in between. An even degree polynomial would have like a start up, finish up kind of scenario, or start down, finish down kind of scenario. And it all has to do with the fact that raising negative numbers to odd powers keeps them negative, whereas raising negative numbers to even powers turns them positive. And how will it depend on whether we go this way or that way? It's whether the leading coefficient is positive or negative, and this one's a positive 1. So because it's positive and because it's a cubic, which is odd degree, that means we'll start down and finish up, which is a way of saying in end behavior terms, as x approaches negative infinity, go left, y approaches negative infinity, we go down. And as x approaches positive infinity, go right, y approaches positive infinity, we go up. Now, when we're plugging in values, make sure to adhere to order of operations. I might not show all the work of this stuff in between. I'll say out loud what the terms are as we add them. But we're actually not graphing to begin with. If we look at the first 2 questions, as I'll begin, numbers 1 and 2, decide whether the function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. So these parts are important when it comes to graphing. You do want standard form. Obviously, they're going to have to be a polynomial if so. And degree and leading coefficient, like I mentioned before, are cruxes of what it is we're going to do to get the graph's end behavior. So in this polynomial, the first thing I want to just look to as a whole, whether I write it in standard form or not, is whether or not it's a polynomial. And this is a polynomial. Every variable is raised to a whole number exponent. This is raised to the 3rd power, the 2nd power, and 7th power. Now, I want to make sure you understand a whole number is every integer, positive, and 0. Negative whole numbers don't count as whole numbers, right? -2 is an integer, but it's not a whole number, so that wouldn't qualify. Obviously, fractions aren't whole numbers as well. Anyway, so these are all whole numbers. This does indeed make this a polynomial. So because it's a polynomial, we'll proceed forward addressing the other things that they asked us, which are rewrite this in standard form. Now, standard form of this will be descending order of degree. We first write the term with degree 7 first. Keep the coefficient exactly as is. And in fact, coefficient's irrelevant when it comes to what order you go. It's all about the degree. Then degree 3 with a -1 coefficient, I. And then this plus 2x squared is the last term. So here's our standard form. Now, it is in standard form that we end up having the true leading term. This -15x to the 7th is the leading term. Therefore, we can refer to its degree of the term, the type of that degree, and the leading coefficient. So the degree of this thing is 7. Now, the important thing for us when we come to graphing this is 7's an odd number. It helps dictate end behavior. So does this part. Type comes next. 7th degree, I believe is, let's see, I just want to say some out loud. 0 is constant, 0 degree is constant, 1 is linear, degree 2 is quadratic, degree 3 is cubic, 4 is quartic instead of quadratic, 5 is quintic, 6 is sextic. I believe 7 is septic. I know that kind of sounds like like sewage or something like that, but it's septic. 8, I think, is octic, things like that. So septic type. If you didn't know that name, I think it's the first time we're actually running across it. But the other important part besides the degree being odd is also the leading coefficient. Now, the leading coefficient as a value is negative 15. The most important aspect for us when it comes to end behavior is that it's a negative number. If we were to graph this thing, it would probably be doing something like that. I don't know how many times it'll turn, but it'll start up, finish down, that kind of thing for the polynomial. Again, not that we're graphing it, but that's number 1. Number 2, P of x equals x cubed minus 5x to the 0.5 power, we're going to have to talk about that, plus 13x squared plus 8. Firstly, we identify whether or not it's a polynomial, and then if it's a polynomial, we start addressing the next questions: standard form, degree, type, and leading coefficient. Now, we spoke on degrees from the previous question. Let's do the same thing again. This is degree 3. I guess we can say degree 0.5, degree 2, and degree 0. Don't say 8. Constant is degree 0. Remember, that would be the same as saying x to the 0 power. So it's whatever your variable is raised to power-wise. Now, this middle term, the second term, x to the 0.5 power, 0.5, is not a whole number. This thing kind of nullifies the idea of polynomial. It goes from polynomial terms here, sure, to actually a radical term. If you know, and if not, we're going to start talking about it in chapter 4, raised to the 0.5 power is also raised to the 1/2 power. Raised to the 1/2 power means raised to the square root, or it means the square root of. So this is negative 5 times the square root of x. It's a radical term. Radical terms cannot, do not, shall not exist in polynomials. Neither can rational terms. Let's say it said negative 5 over x, or negative 5 times the sine of x, or negative 5 times the log of x, or whatever these things are. These don't exist in polynomials. These aren't with variables raised truly to the positive powers, or 0 power. So this is not a polynomial. And because it's not a polynomial, we actually don't have to address anything else about it. Standard form, I'm not going to say is moot, but because we're not addressing that, right, it would maybe be moot in some of our graphing senses. There are still ideas of standard form we could do, but we're going to leave it. We're going to leave it. Not a polynomial. We move on. Okay, numbers 3, 4, and 5 are where we actually do the graphs. Now, we will be using a table for these, especially as we haven't yet covered factoring, not until section 3, 4, or something like that. And some of these aren't factorable. And, I mean, just a lot of things about it. We'll use the table. We'll understand what these things are. And then later, we might do some tableless graphing. We might use the graphing calculator to get some of the graphs. It depends on what kind of question they're asking. All right. H of x equals x squared plus 6x to the 5th minus 5. Now, the first thing you're going to want to do here is rewrite it in standard form. Again, what we did in the first 2 questions was not irrelevant. I repeat, it was not irrelevant. Totally relevant to what we're doing. Let's build a table. Now, they went from negative 3 to 3. We did a lot of negative 2 to 2. When it's to the 5th power, I'd say that number's going to skyrocket pretty high to the point that I think these numbers will be enough. I don't know for sure. And if they're not, we'll go from negative 3 to 3. All right, let's start with x equals 0. That becomes 0 plus 0 minus 5, which is negative 5. It's the y-intercept. We should get pretty used to that one. We plug in 1. 1 to the 5th is 1. 1 squared is 1, things like that. So this becomes 6 plus 1 minus 5. 7 minus 5 is 2. Now 2. 2 to the 5th. And remember, order of operations. We do exponents first and then multiply second. 2 to the 5th, 32. Times 6 is 192. Plus 4 is 196, minus 5 is 191. I mean, that's tall. It's tall to the point that I don't know if I really want to plot that as as a point to actually be able to graph. It'll be kind of icky. I'd rather plug in 1.5, and even then, it's probably something very tall as far as my window range goes. Negative 1, let's go backwards. Negative 1 to odd powers will be a negative number, so that'll become negative 6. Plus negative 1 squared is positive 1, so that's negative 4. Minus 5 is negative 9. And then negative 2 to the 5th is negative 32. That's negative 192. Plus 4 is negative 188. Minus 5 is negative 193. So even the negative 2 to 2 are even crazy numbers. Now, there are things that fifth power polynomials can do that even cubics can't, but within there are possibly twists and turns. And I can't guarantee what's in between. I'd almost want to use the graphing calculator to figure out what it actually is. But what I do have for now, at least, is a -5 here, a 2 here, sorry, a +2 here, and a -9 here. Now, this is not linear. I know it kind of appears linear. It is entirely possible that the graph just does, which is very sharp, guys, that this graph just does something along the lines of this, along the lines, no pun intended, as it's not linear. It might do something like that. Again, this is not linear. What's going to happen is it'll go toward its straight downturn. Remember, at -2, we hit -192, so it goes very low. Maybe I have to change the scaling. It's also possible, given a fifth degree polynomial, and I don't know, I think I might have to check the graphing calculator with this, guys. It's very possible that as this is going up from -193, so it goes up from -193, it might take some sort of eccentric turn here, and some eccentric turn right here, and stuff like that, and shoot back up. Fifth degree polynomials could do as much as that, even cubics can, so I'm actually more interested in looking at, which it might not do those, but I want to look at it on the graphing calculator, if you don't mind. This is one where chapter review, I slow down a little bit more. Chapter test, I don't as much. If something piques my curiosity to get something right, I'll do that. They generally wouldn't expect us to plug in decimals to get results, and I'm not going to try to here. So I'm going to let my graphing calculator do it for me. Let's substitute in 6x to the 5th plus x squared minus 5. And if I just go to this part, just from here, okay, you see a lot more of a turn on that thing. It doesn't turn around like that, but it does turn into the y-intercept a heck of a lot. If I increased my window from -200 to +200 and took a look at the x values a little more minutely to -3 and 3, you'll see more gradual essence of this curve. You can see it just kind of curve down and curve up like that. So it plateaus to going up, which is all that it does. It doesn't have the eccentric turns that I said it could potentially have. But I do want to get that nature of it. Let's go ahead and give that one a shot. So from here, again, it's going down toward -193 when x equals 2. Let's not try and cross the -2 threshold. But let's go up and let's kind of curve through instead the y-intercept like that. And then we'll go up through when x equals 1 and hit that guy as well. So normally I don't slow down on graphs like that, but just for the sake of our first one and me not knowing for sure what's going to happen and only having 3 points to talk about, that'll be it. Now the other things I want to mention, although the points probably took care of themselves to show you this, are end behavior. This is a fifth degree polynomial. That means odd degree. That means it'll either start down, finish up like this did, or it could have started up, finish down. The leading coefficient was a positive number, which was telling that the fact it would start down, finish up. That's what odd degree positive leading coefficients would do. As far as end behavior goes, I would say as x approaches positive infinity, y approaches positive infinity. And as x approaches negative infinity, y approaches negative infinity. Now, they didn't request this information, but I don't believe that they're going to later as well. So I want to make sure that you're getting instances of this when we do these graphs. Plus, it helps explain why the end behavior is what it is. Okay, let's go on to number 4. F of x equals 3x to the 4th minus 5x plus 1. It's already in standard form. I said 5x squared plus 1. It's already in standard form, so I'm going to graph as is. Let's go straight to our table, xy. Let's start with 0 again, classic. Plug in 0, you get 1 out, your y-intercept. Plug in 1, you get 3 minus 5 plus 1. That's negative 1. 2 to the 4th is 16 times 3 is 48. Minus 20 is 28. Plus 1 is 29. Also pretty big. Maybe this is one where I could maybe scale by 2s, if it seems fair. I think I might go for that, depending on what these numbers are. Negative 1 to the 4th. Listen, negative 1 to the 4th, negative 1 squared, those are still positive numbers. You're going to still be left with 3 minus 5 plus 1. This also is negative 1. Negative 2, we still get this same stuff. Positive 48 minus 20 plus 1. It's still 29. This is, we might be able to talk about this one later, but this is what is known as an even function. It has symmetry across the y-axis, which means you're going to get the exact same thing on the left side as you do on the right side. I'm sorry, you didn't see that 29. It was cut off, my bad. Anyway, that was a 29 there. Let's go ahead and begin this graph. I think I want to hit the 2's this time and not just pretend like we didn't. So let's go by 2's. This will be 10, 20, and 30. If we are going by 2's, keep in mind that we're doing it on y's. On x's, we'll stay the same, 5, -5, like that. Keep in mind that when x is 1, or when y is 1 or -1, or all these are odd numbers, we're going to hit halfway between any increments here. So 0, 1 is actually not here anymore, but it's down here just because of the change. 1, -1, and -1, -1 are here. And 229, -229, here's 30, here's 28, so 29 is right in between like these. You're going to get a bit of a W shape here, and to hit home what this thing is, again, it's a quartic function. It's not a quadratic, but a quartic function. And in a quartic function, not only can you have this kind of turnaround like this, and it's not angled, so to speak, there's a curve to that, which I'm trying to do the best I can on that one. It's very sharp still, and this is a less tall version of the graph. But with this thing here, it can do that, but it also has, this is symmetry just because it's an even function, not even degree, but exactly even function here. This can have these many turnarounds, and it has the end behavior going, starting and ending in the same direction. The degree is even. The leading coefficient is positive. So there's the start up, stay up kind of scenario. As far as end behavior goes, as x approaches positive infinity, y is approaching positive infinity. And as x approaches negative infinity, y approaches positive infinity. Again, this is end behavior. This is as we go toward infinity. In between, there's some other stuff that can happen, such as what you see right here. But that's what we see as a whole on number 4. Then number 5, g of x equals -x to the 4th plus x plus 2. Once again, it's a quartic function, so you might see more of the same. It might not be fully as symmetrical as last time. This doesn't actually appear to be an even function because that middle term. But let's go and substitute our numbers. Let's see. We're probably going to get a similar-esque looking graph. Maybe not quite as tall. But x and y, let's substitute these, see where we go. We plug in 0, we get 2. 1, we get, remember, you do 1 to the 4th first, then you turn it negative. So -1 plus 1 is 0, plus 2 is 2. So these are the same. Maybe something happens in between. Substitute 2, you get -16 plus 2 plus 2. It's -12. Now on the other side, -1 to the 4th, opposite of that is still -1. -1 minus 1 happens here, which is -2 plus 2 is 0. And this becomes -16 minus 2 plus 2, which is -16. So not perfect symmetry. Maybe a shift over in some sort of way. Let's go ahead and take a look at what this graph may look like from these points. Now, given the negative leading coefficient, still an even degree, but given the negative leading coefficient, this time we're talking about start down, finish down kind of end behavior. So get ready for that. 1, 2, -1, 0, -2, -16, and this is all the way down here, and then 2, -12. Now, it's possible, and perhaps likely, and I won't look on a graphing calculator, but it's possible. It doesn't have any W-shaped stuff. It kind of just has more of the U shape and does the turn. Remember, quartic functions can be that, similar to quadratic, where they can be parabolic in nature. It might do less as a whole when it comes to, say, this turn, but it goes much sharper ultimately after this. And I'm keeping these scales as 1s this time because I can fit all these points just fine. Now, they will finish downward this way. That is the end behavior of a, once again, negative leading term, quartic function. That was a swing and a miss on hitting that point. Let's pretend like I got it right there. All right, so maybe that's the appearance of that graph. I'm going to go ahead and leave it as is. Let's go ahead and once again identify. Degree is 4, which is even. Leading coefficient is -1, which is negative, which has the start down, finish down, end behavior, which I'll write here. As x approaches positive infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches negative infinity. So it's both ways that we're looking at that. Again, those aren't asked for, but those are just a reminder of what it is that we have when we graph. Okay, let's move on to section 3.2 on adding, subtracting, and multiplying polynomials. I don't have much to teach in this sense until we hit the binomial expansion problems or even these cubics right here, because everything else we would have seen probably in IM2. So we're going to multiply these 3 together in a horizontal format, and I generally go horizontal anyway. What they're showing in color coding format is they do 2 at a time. I generally do the last 2 at the same time, but it doesn't really matter. Multiplication is commutative. You can go any order you'd like. Multiply these first two to FOIL it out. Try not to do all three together. Even I can't do that in one fell swoop. You'll make a mistake. It's probably not what you think it is when it comes to distribution. Anyway, so then you have this one, and then you multiply red by blue, and they're doing their own form of looking at distribution. X multiplies by these three. 3 multiplies by these three. You end up getting these. You combine like terms, you get this polynomial here. So we're going to do probably some of that. I see it on number 11, so get ready for a question like that on all things FOILed. And then we're talking about Pascal's triangle to expand this. Now, Pascal's triangle is something that I'll probably build with you when we get to the questions like it, where we have to do the expansion. But they're talking about the coefficients of the fourth row of Pascal's triangle are 1, 4, 6, 4, 1. These are the numbers that you multiply, 1, 4, 6, 4, 1, by your other items in each term that appear as a result of the triangle. This is row 4. That's why we're doing the fourth row. Now, your binomial inside of here, 4x is like your A and 2 is like your B. We first raise a to the fourth and b to the 0 power, which is 1. That's why you don't see it here in the first term. Second term, you raise a to the third power, b to the first power, then a to the second, b to the second, a to the first, b to the third, and a to the 0, b to the fourth. They trade places, and those degrees always add to 4 as long as it's the fourth row. If we do a to the fifth power, they're always going to add to 5, but they go from ascending to descending order and kind of flip around as we multiply by these coefficients. Anyway, you get everything multiplied out, you get this quartic as an expansion, which is indeed the fastest way to go about a problem like that. So let's start with numbers 6, 7, and 8, all which have nothing to do with those two examples, I think because they're probably easier versions of problems and they have only so much time to teach something, and I think what they taught was just fine. So we're going to start with a subtraction problem where we have subtracting this polynomial here. Excuse me. It is now expected, I don't know if it's just an implied thing or whatever word to infer it. It's expected that from here on out, we're always writing our answers in standard form. They generally present these in standard form. Not always, but I think you can mostly expect them to. But make sure you finish it off in standard form. Anyway, I'm going to begin with a rewrite without parentheses. This negative needs to distribute into these three terms here, which changes signs. Subtracting a negative becomes a positive. Subtracting a positive becomes a negative, and so on. And from here, we can look to combine like terms. I find any other cubics. They're not here. 4x cubed is the end of that degree. Quadratics, we have negative 12x squared plus 8x squared. Negative 4x comes next when it comes to standard form. And negative 5 minus 3 is negative 8. I actually expected a 4 just because all the other ones were 4s. Making sure I did all the work right there. Looks good. That's number 6. Number 7, we have arguably easier than subtraction, but the same stage after the first step, addition. In fact, I'm going to write this right now without copying down the original parentheses. I'm just rewrite without parentheses, x to the fourth, 3x cubed, negative x squared, and then plus 6. The plus does not turn things positive. It keeps things as they were. So adding a positive will be addition. Adding a negative will be subtraction. And adding a positive is addition. So rewrote without parentheses as the problem's already copied down there to begin with. Now we combine like terms. X to the fourth is the largest degree, and there are 2 of them that can add together, which become 3x to the fourth. The x cubes, only 1 term there. Maybe everything will turn into a 3 this time. Negative x squared looks like it stands alone. X terms, this one stands alone, and 6 plus 9 is 15. So no, not everything turned into 3s, or multiples of 3. There should be your final result in number 7. Number 8 is subtraction once again. So we're going right back to it. Let's see if I can, again, do the copy it down without copying down the part in parentheses. Let's rewrite it without parentheses already, straight up. But I need to make sure to distribute that negative and change all the signs in the second quantity. So we're going to subtract the positive, subtract the negative, and subtract the positive. So do more of the same, combine. And see, it's at this stage that we treat it just like the addition problems. There's now no difference because the subtraction is no longer subtraction anymore. It's just treat the signs as they are. Combine like terms, write in standard form. You're good to go. All right, there are numbers 6, 7, and 8 finding the difference. I wrote them in standard form. We have now 9, 10, and 11 where we try and find the products. This is mostly any form of just multiplying each term in one quantity by every term in the other quantity. And then we combine like terms. Make sure you're in standard form in the end. I generally like to multiply the binomial times the trinomial, and it looks like the book kind of did that as well. I'm going to multiply y by these 3 terms, and then I'm going to multiply 3 by those 3 terms after. So multiplying these by y will increase their degree by 1 each. The coefficients stay the same. So that's a 7y now. Oh, this is 4y squared. I don't know why that just happened. And then let's multiply 3 by these 3 here, which keeps the degrees as they are, but it triples your coefficients. 6y squared, 12y, and negative 21. Now we combine like terms. Y cubed, again, stands alone. It's in the lead. 4y squared plus 6y squared is 10y squared. Exponent stays the same. Negative 7y plus 12y is 5y, and there's that minus 21. So this is the standard form, expanded, simplified version of that product of polynomials. Number 10 is an instance somewhat that you can use Pascal's triangle for, and I'm not saying you can't at all. You probably should. There is a formula that was introduced in this section, though, treating it like a special case. Sum of two cubes, difference of two cubes. These things right here. Sorry, not sum difference of two cubes. That's a different thing entirely. I'm sorry. Cubed binomial, whether added or subtracted. Now, let me write out what the formula itself is, and this does have to do with, again, the Pascal's triangle thing. A plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared minus b plus b cubed. I think it's probably one of the last ones that they assume you know over time at some point, but if you want to use Pascal's triangle, go ahead. And in fact, as I stated, this is Pascal's triangle. It's 1, I tried to use purple. It's 1, 3, 3, 1, that's the third row in Pascal's triangle, multiplied by a cubed b to the 0, a squared b to the first, a to the first b squared, and a to the 0 b cubed, like that. So follows the same notion we're going to have to do on numbers 12, 13, and 14, just giving you a little heads up there. So let's go ahead and give this one a shot. 1a cubed times b to the 0 is just 2m cubed. That's your first term. Now 3 multiplies with 2m squared and n to the first power. And then 3 multiplies with 2m to the first power and n squared. And then n gets cubed here. That's not the end. We got to do more simplification. One thing I want to mention before I move on here, because I didn't actually show it, is that if this was a minus, that would mean the negative term getting raised to odd powers, in this case, would turn this into a minus and this into a minus right here. They basically alternate signs as you go down your list. So there's that beginning portion. I probably should have done this on the bottom, right here, here, and here. Anyway, so let's get rid of this thing in blue and purple and whatever all those things are, and let's continue on to the problem. Whoa, I lost my problem. What just happened? What just happened? I think I went down to the very last page. I must have hit end. All right, so let's go back to this. We have 2m quantity cubed is 8m cubed. 2m squared, 2m quantity squared is 4m squared. 4 times 3 is 12. And now we have m squared times n. 3 times 2 here is 6. We get 6m times n is squared. And n cubed is exactly just that, n cubed. And this is your final result. Now, when it comes to standard form, sometimes in these ones, we'll just keep them kind of as they were presented. It depends on the problem. However, I would still argue this is standard form. If you know anything about degrees here, this is degree 3. Degree 2 plus 1 is 3. And these are all 3. 1 plus 2 is 3, and this 3 is 3. So when there's a tie, how do you know which terms to write first or when to reshuffle them? My argument here is m is alphabetically first, so we call it the alphabetically dominant term. Therefore, you go by its degree when there's a tie. This is degree 3, 2, 1, and 0, and so we would go by that one to order there. Despite the fact that the n's are there, it's just because it's a tie. Okay, that was a bit of a different kind of teaching that was kind of in this portion right here for binomial expansion, but using that one formula. Let's go on to number 11. Number 11, we have s's. Thankfully, no 5s conflicting at the moment. I don't like s's with 5s. They generally tend to put them together. I'm going to start by multiplying these two together, and then I'll deal with the s plus 2 with that afterward. So this begins with FOIL s squared minus 3s plus 4s is plus 1s, and then minus 12. 4 times negative 3 is minus 12. Now we work on these the same way as we did the other set. S will distribute into these 3, and then 2 will distribute into these 3. So we'll get s cubed plus s squared minus 12s plus 2s squared plus 2s minus 24. When you combine like terms in standard form, you get s cubed plus 3s squared minus 10s plus minus 24. Minus 24. So no 5s going in the way. That's actually probably a first that I didn't see even a single 5 in this, which is incredible. Okay, that was numbers 9 through 11 with multiplication, and now we'll use Pascal's triangle or the binomial theorem to expand the binomial. Binomial theorem is Pascal's triangle in a way, but they use combinations to build Pascal's triangle. Pascal's triangle is this. Row 0 has a 1, row 1 has 2 1s. Everything will have 2 1s here on out, but in the middle, row 3, or row 2, I should say, we'll add these 2 1s together to get 2. Row 3, we'll start adding these ones in between as the ones are on the outside. 1 plus 2 is 3, 2 plus 1 is 3. There's all symmetry in the triangle, in Pascal's triangle. We need to go up to row 6 for the sake of what we have. Here's row 4, what they mentioned before. 1, 4, 6, 4, 1. Again, it's the addition of the values in between. And you can build this pretty easily as you go. You can always rebuild it as well. How deep do you want to go? Generally not much past row 6 or 7. Row 5, 1, 5, 10, 10, 5, 1. And row 6, 1, 6, 15, 20, 15, 6, 1. Now we're going to need all of these for these. We are going to start with raising to the 4th power, so we need row 4, and then 5 and 6. Let me do one more thing here. Let's just name them by row. I'll do it in purple. Row 0, or I guess that's black. Where's purple? Row 0, 1, 2, 3, 4, 5, 6. 0 does matter as far as like naming the top one 0 is kind of important instead of calling it 1. It's based on what power we raise to. When we talk about combinations and things like that, there are a lot of different reasons for which you're going to want to know what it is. Sorry if you can't really see that much, but I'll have to say them out loud. Now, what they have to do with the problems, of course, like I stated, is they are the coefficients, the beginning part of the coefficients that multiply by whatever your terms are as you begin your problem. So number 12, we have m plus 4 raised to the 4th power. So we're going to use 4th row, which is 1, 4, 6, 4, 1, as our 5 terms. Row 4 is 5 terms. 1 times m to the 4th power times 4 to the 0 power is just that, plus 4 times m to the 3rd power times 4 to the 1st power, goes here, plus 6 times m to the 2nd power times 4 to the 2nd power, plus 4 times m to the 1st power times 4 to the 3rd power, plus 4 to the 4th power. 1 times m to the 0 power times 4 to the 4th power. Now we clean it up. 4 times 4 is 16, so we get 16m cubed. 4 squared is 16 times 6 is 96. 4 cubed is 64 times 4 is 256. And 4 to the 4th is also 256. So here's the binomial expansion of this one raised to the 4th power. And I just need to state this now just so we understand. M plus 4 to the 4th is not just m to the 4th plus 4 to the 4th. Yes, those are the first and last terms. Boom, boom. But you're missing a bunch of terms in between. It's not as easy as that. And you can't really do anything much easier than what we just did, or much more efficiently. That is the most efficient practice. Otherwise, we probably wouldn't do it. Number 13, 3s. Oh, here's an s with a 5. 3s plus 2 to the 5th power. They didn't let us off the hook that easy. Now, yes, these get a little big. These are a little exhaustive. They take a little while. I remember when doing this section, and I'm having PTSD of coming back to it. Thankfully, there are only 3 of them in total, and we're only going as far as to the 6th power. My PTSD now is with an s and a 5. All right, so we're going to use the 5th row, which is 1, 5, 10, 10, 5, 1. So the first 3 terms, we're going to first raise 3s to the 5th power. That's the 1. And then 5 is times 3s to the 4th power, as we multiply 5 to the 1st power. And then the third term is 10 times 3s to the 3rd power and 5 to the 2nd power. Remember, your exponents always need to add to 5, the same as the degree that you have here. Now we have 3 more terms, another 10 times 3s, this time squared, and 5 cubed. No shame in using a calculator in this multiplication, by the way. I might have to as well. We'll see. Plus 5 times, and I noticed all of these are pluses. They never turned any to minuses. It's kind of too bad when it comes to this review. I would have been nice to do at least one of them. 3s to the 1st power and 5 to the 4th power, plus 5 to the 5th power. Because they never spared me at the time using a bunch of negatives, so I mean, we might as well practice with them as we're probably reviewing for a test or something like that, right? 3 to the 5th power, guys, is pretty big. It's 243. 243 times s to the 5th power is your first term. But all these numbers should be big. 3 to the 4th is 81. We got to do times 25. 81 times 25. I don't know what that is. 2025? Let me check. 81 times 25. 2025. All right. Times s to the 4th. 3 cubed is 27. 5 squared is 25. 25 times 27 is, I think, 675. 675 times 10 is 6750. 6750. S cubed. I need to double check that. 27 times 20. I shouldn't have to. 675, yes. I was always better at multiplication than I was at addition. I mentioned that in the last section, section 3.9, where I made addition and subtraction mistakes quite often. 9 times 125 is going here. I think that's 1,125. So times 10. 11250. Numbers are just getting bigger, y'all, as these S's are getting a little smaller. Plus, 5 to the 4th is 625. We got to do 625 times 15. I don't know if I can do that. Let's do 3125. 3125 times 3 is 9,375. I'm going to go with that. Sorry if these are mistakes. I mean, I'm going to double check all of these. And 5 to the 5th is 625. I'm going to check that. Maybe it's 15. Maybe 15625. 15625, not 16. 15625. I'm trying to fit them all in one line, because that would then be the final answer if I got all those right. Let's check on those. 9 times 125 times 10. 11,250. Okay. 5 to the 4th times 3 times 5. Sorry for stalling on this. I want to make sure 9,375 and 5 to the 5th. Oh, 5 to the 5th is 3125. I take it back. 5 to the 6th is 15,625. I was in the wrong camp here. Okay, this one's just 3125. I'm sorry. I probably should have recognized these numbers were getting smaller again, and I should have checked on that. So it's a good thing we double checked there. That next number, I believe, is 5 to the 6th, however. I was just in the wrong counting. Let's check 5 to the 6th. 15,625. Okay. All right, let's jump to number 14, the last one of these. And it may look a little treacherous given this is the 6th power. However, it is just z plus 1, which is nice. And again, I really wish we had a minus on one of these. I almost want to change it to z minus 1. But let's look at our coefficients. We need 1, 6, 15, 20, 15, 6, and 1. The good news is that's as small as these numbers are going to get. They're not going to multiply by anything else because 1 is just a 1 even when raised to other powers, and z is a coefficient of 1. So 1, 6, 15, 20, 15, 6, and 1. So it starts 1 z to the 6th times 1. Listen, the 1s don't change anything. 1 to any power is just 1. So when it comes to multiplication, it won't change a thing. I'm actually not going to write it. The only thing 1 will need to do and be is be in the last term. We have to add 1 at the very end. So z to the 6th plus 6 times z to the 5th times 1 plus 15 times z to the 4th times 1 plus 20 times z to the 3rd times 1 plus 15 times z squared times 1 plus 6 times z times 1 plus 1 to the 6th power, which is just 1. This is the final answer. This is standard form. We are all set. That's number 14. And that's the quickest binomial expansion you can do for something that's quite so massive. Those were the coefficients there. All good to go. All right, let's move on to section 3.3 on dividing polynomials. There are two types of division that we learned. There was long division and synthetic division. Here they are showing synthetic division on a problem. I'm sure we're going to do some long division. We'll take a look at that. But synthetic is the better visual of what they want to talk about. -3, I tend to put a little box right there and a little box right there with this line. But -3 is our root. They're saying when x is -3. That means as a factor, if you were dividing, we're dividing by x plus 3. I want to keep that in mind, that it's the opposite of that sign when it's a root, things like that. Synthetic division can only be used on linear factors. Synthetic division is lovely. Absolutely lovely. But it can only be used in certain scenarios. We'll try and use it when we can. We write out these coefficients. They need to be, once again, in standard form. If there's ever a missing term, as in if there was no squared term, you'd have to write a 0 as a placeholder. 0x squared, something like that. but we don't write the x's. Now we're going to bring down the negative 2 multiplied by negative 3. Negative 2 times negative 3 gives you 6. Add these together to get 10. Multiply that by negative 3 to get negative 30. Add these together to get negative 22. Multiply those by negative 3 to get 66. Add these to get 76. You divided a cubic by a linear, so you're left with a quadratic. This is now your quadratic term. This is your linear term. This is your constant term. And 76 is your remainder. Now, when they said use synthetic division to evaluate this, they didn't actually they didn't actually do it as division, and they didn't actually write that result because they're talking about something else. So let's first just talk about the result of this. That division divided by x plus 3, right? That equals negative 2x squared plus 10x minus 22. Now the remainder is 76. That actually means 76 over that x plus 3, the coveted x plus 3 that I had to introduce in the problem. Okay. Now, that being said, they said evaluate this when x equals negative 3. The idea of this is when you substitute negative 3 into a polynomial that if you multiply everything by x plus 3, hard to explain, but when you substitute negative 3 into here, you're going to be left with the remainder of 76. That's why using synthetic division can assist you on that. You can use synthetic division to determine the remainder, and the remainder is the result. Because I'm missing a portion of this by multiplying everything by x plus 3 to show you what happens. But when we do division, that's what we're getting, something like that. All right, so there's an idea of synthetic division. We'll also do long. I can see the first problem might be a good time to use some form of long division. So let's see what that looks like. Divide using polynomial long division or synthetic division. Number 15, we have x cubed plus x squared plus 3x minus 4. This is the dividend. We divide by the divisor, x squared plus 2x plus 1. And we should get a quotient as a result, possibly with some remainder. So using long division, what we have to do in these cases is we have to take the leading terms, and they have to be in standard form, but take the leading terms of both polynomials and find out how many times one goes in together. X squared goes into x cubed just x times. Now you multiply x squared by x to get x cubed, 2x by x to get 2x squared, and 1 times x to get x, and you subtract the result of this from that. X cubed minus x cubed is 0. X squared minus 2x squared is negative 1x squared. 3x minus x is 2x. And the negative 4 minus 0 is negative 4, so that just goes down like that. Now, notice it was subtraction. I don't visually write things like subtraction. I don't do this. I don't change the signs or anything like that. I'm well aware of what I'm supposed to do. Normally, people are okay with it. Just be careful when you subtract negatives or subtract from negatives. Now, these are all positive. They're kind of being nice to you again with that. X squared goes into negative x squared, just negative 1 times. X squared times negative 1 is this. And these should cancel out ultimately when you got that. 2x times negative 1 is this. And 1 times negative 1 is that. Now, negative x squared minus negative x squared is negative x squared plus x squared, which is 0. Do not cancel these out. This isn't 2x minus 2x. It's 2x minus negative 2x, which is 2x plus 2x, which is 4x. And negative 4 minus negative 1 is negative 4 plus 1, which is negative 3. Now, x squared cannot go into 4x. This is a higher degree than that. So it's at this stage that we stop. This is the quotient. This is the remainder. This is the q. This is the r, if you will. So when we're dividing that and asking for the result of what this thing is, when we divide these two, here's the answer. It equals x minus 1 with the remainder of 4x minus 3. We put as plus 4x minus 3 all over x squared plus 2x plus 1. The thing that it couldn't divide by, it's still dividing by, right? If I do 10 divided by 4, no, let's say 11 divided by 4, 4 can go into 11 twice, and 11 minus 8 is 3. 3 is the remainder. That's 4 plus, twice. That's 2 plus 3 quarters. 2 plus 3 quarters. 2 remainder 3 is 2 plus 3 quarters in that scenario. Okay, let's move on to number 16. Now, on number 16, we'll once again use long division because, again, we do not have, what don't we have? We don't have a linear factor. Excuse me. Okay, so in this case here, we'll do the same thing as we did last time. X to the fourth plus 3x cubed minus 4x squared plus 5x plus 3 divided by x squared plus x plus 4. X squared goes into x to the fourth, x squared times. Where you multiply those, we get x to the fourth. x times x squared is x cubed. 4 times x squared is 4x squared. Now we subtract results. Don't forget, it is subtraction of the results. So 3x cubed minus x cubed is 2x cubed. Negative 4x squared minus 4x squared is negative 8x squared. Bring the rest down. We keep going once again until we reach a degree 1, or degree 0, reach a degree that x squared can no longer go into. So we should at least be able to do this 2 more times. X squared can go into 2x cubed 2x times. X squared times 2x squared is indeed that 2x cubed. And we got 2x squared and 8x. We subtract again. And we get negative 10x squared and negative 3x. And the last one that we're going to be able to do before we hit remainder status, unless this doesn't have a remainder, you never know. X squared goes into negative 10x squared negative 10 times. And so now we'll have negative 10x squared minus 10x minus 40. Total remainder status. Absolutely. They don't often do ones that don't have remainders on these. Now this is 7x because we're subtracting the negative, and same thing here. This is plus 43. X squared can't go into 7x at all here, so we're left with this quotient and this remainder. So that all equals, in the end, minus 10. I write too fast. Plus 7x plus 43 all over x squared plus x plus 4. Remember, the original divisor is still in play and the remainder portion. Okay, number 17. This is one where you can use long or synthetic division. In this case, I will use synthetic any chance that I get. So we have x to the 4th minus x squared minus 7 all divided by x plus 4. Now, this one has a linear factor, therefore it is in use. If x plus 4 is the factor, then negative 4 is the root. So in synthetic division, I'll place negative 4 in the corner. I got a 1x to the 4th, 0x cubed, negative 1x squared, 0x, and negative 7 as the constant. You have to build it down that way to get properness in what you're going to need. So 1 comes down, multiplies by negative 4. You add these together, multiply by negative 4, and so on and so forth. This continues, and you get this big 240, and you get a big 233 remainder. Sometimes I don't trust that kind of stuff. I say, oh, what's going on? It's kind of tough to tell. But it is what it is, right? It was a quartic, now it's a cubic. The result of this one is 1x cubed minus 4x squared plus 15x minus 60 with a remainder of 233. 233 is still dividing by that x plus 4. It couldn't divide by it, and that's what we get as the result. So synthetic division, again, it is a form of long division, or it's a quick, I don't really know how to say it. It's a shortcut of long division that allows you to skirt past things like needing to use x's or needing to do subtraction, because we're doing addition instead of subtraction by multiplying by the root, which is the opposite sign, if you notice. And we, as long as we put placeholders as zeros for coefficients for the x's, it'll recognize we're going from a quartic to a cubic, and that these will go in for the squared and the linear, or the cubic and the linear. Now this is the squared and the constant, things like that. So it's all in play. It all works out. It's all good, and we're using a lot of it, especially down the line. That's why I wanted to do it here. Number 18. Use synthetic division again to evaluate g of x equals 4x cubed plus 2x squared minus 4 when x equals 5. Now, there are technically two ways to do this. Only one way if they say use synthetic division, but if you want to evaluate when x equals 5, just like table use, we can substitute 5. Let's see what happens when we plug in 5. 5 cubed is 125 times 4 is 500. Plus 25 times 2 plus 50 is 550 minus 4 is 546. So I expect to get 546 from this. Now let's use synthetic division on the same thing to get that same result. When x equals 5, let's go ahead and do that. The remainder will be our result. Our remainder should be 546. Let's take a look. 4x cubed, 2x squared, 0x, negative 4. Bring the 4 down, multiply by 5, and add, and plug and chug. So this is the remainder. This is the remainder. The remainder is the result, given remainder theorem. There it is, 546. Okay, that's section 3.3. Now we go to factoring in section 3.4. Now factoring, again, is something of old that was done quite often in IM2, to a large extent even. This is where we do some sum and difference of two cubes factoring as well. I'm trying to think of other things that we have. Oh, these are ones where we are... Oh, we're determining whether something's a factor of something or not by using synthetic division. If you get a zero remainder, then it is a factor of it. That's a test that you can do as well. So there are two different things that they have on here. Part A, factor this completely. In terms of factoring completely, you're looking for common factors first and always. And then you're left with this. In this case, you have a sum of two cubes. X cubed is literally that. 8 is 2 cubed. So A plus B, A cubed plus B cubed factors into A plus B times A squared minus AB plus B squared. Probably something I can write out if we run into our own, but there's that one. The next one, again, determine whether this is a factor of that. Use synthetic division and figure out if you get a remainder of 0. If you do, that means it's a factor. And it also means you might be able to factor completely as a result of what you have. So you kind of have tests and what you can do on that. And as you do your synthetic division test, you're actually reducing your polynomial, which kills two birds with one stone. It's a good thing. And if it doesn't factor, then you stop factoring. All right, so let's start with number 19. Number 19 is what's called a difference of two cubes. I have a perfect cube here and a perfect cube here, but even more so, I do have a common factor, and I want to begin with it because you don't want to forget the common factor. 8 can factor out of here, and you're still left with a perfect cube in 8 and a perfect cube in 1, so nothing's hurt. Nothing's hurt. 8's going to stay on the outside of whatever we do, by the way. This is 2x cubed, and this is 1 cubed. Now, a cubed minus b cubed factors into a minus b times a squared plus ab plus b squared. So this is what we're going to do here as well. We have to do 2x cubed minus 1 cubed. Remember, that's not factorization that we did. We just represented this as a difference of two cubes. So let's factor it. 8's on the outside. We're going to start with a minus b times a squared, 2x squared is 4x squared, minus a times b plus b squared, and 1 squared is 1. 4x squared minus 2x plus 1 cannot factor further. You will be done with that. Okay, number 20. Number 20, I already see a common factor, not just by number, but also by variable. Let's go ahead and take a look at what we're doing on that one. We have 2z to the 5th minus 12z cubed plus 10z. They all have z's in them. Factor that out, but they all can divide by 2. Factor a 2 out, you're left with z to the 4th minus 6z squared plus 5. So 2z will remain factor out no matter what we do from here. This is not a quadratic, but it is in quadratic form. Z to the 4th can be represented as z squared squared, and this in itself is z squared. So treat whatever you would as just z's in your factorization now as z squareds, if you will. And as you would do if they were just z's, we're trying to find two numbers that multiply to 5 and add to negative 6. Those are negative 5 and negative 1. We would be done with factoring if there was no more to factor. However, this, not this one, this is not a difference of two squares. This is a difference of two squares, and that factors into z minus 1 times z plus 1. It's one of those special cases. The reason why the first one's not a difference of two squares is because 5 is not a perfect square. I guess you could write z minus root 5 times z plus root 5, but that's not what we're going for with factorization. Integers. Integers. And that's your final factorization of completeness. Number 21. Number 21, we're doing something called factoring by grouping. Something you would have learned probably in the depths of IM2, and if not, we were doing it quite a bit this chapter. There was no loss for which we didn't do it. Group the first two terms by the greatest common factor. Group the next two terms by the greatest common factor. The goal in this scenario, if they give you a problem that works like this, is that when you factor the greatest common factor of both terms, you're going to be left with an inner quantity that exists as the same in both terms. Here I can factor out a negative 4, and I'll be left with 2a minus 7. And what you can tell here is the 2a minus 7s are identical factors in both bigger terms right here. Both bigger sets. If you factor 2a minus 7 out of both terms there, you're left with a squared minus 4 in the other set. Nothing went away. Nothing went away. This was factored out. This was factored out the same way that an a squared was factored out of here and negative 4 was factored out of there. Now, a squared minus 4 is once again one of those difference of two squares. This factors into a minus 2 times a plus 2, and there's the 2a minus 7. And you are good to go. There's the complete factorization of number 21. The last one in this section, number 22, says show that x plus 2 is a factor of f of x equals x to the 4th plus 2x cubed minus 27x minus 54, and then factor completely. Okay, hold on. I smile because reasons. I smile because generally I'd wish that they presented a problem to you that wasn't factorable by grouping. See, we're going to test x plus 2, see if it's a factor. They want you to use synthetic division, get zero remainder, and don't worry, we're going to do that. But first I want to do factor by grouping one more time and say, you know how I can also show you x plus 2 is a common factor? And maybe they're okay with you doing this. Factor out, find the common factor of the first two terms, and find this common factor of the next two terms. Check this out. X plus 2 is the common factor there. X cubed minus 27 times x plus 2. So there's a show. There's a show that it is. Whoops, I tried to use green. So anyway, I didn't finish factoring, and I will. We're going to get to this stage as well. I want to show you that we actually do get here in the same way. So if you can factor by grouping, guys, I'd always encourage that you do it. What they're asking you to show is x plus 2 is a factor by using synthetic division. Negative 2 is the root. We got 1x to the fourth, 2x cubed, 0x squared, negative 27x, and negative 54. Once we get the zero remainder is that show. When they ask you to factor completely, they want you to keep going on the factorization. That includes what we have here. Put in 1, substitute negative 2, or multiply by negative 2, add, multiply by negative 2, add, multiply by negative 2, add, multiply by negative 2, add. Now, this is the remainder. That remainder is our check that x plus 2 was indeed a factor by using its root on synthetic division. This is the remainder. This is the constant. This is the linear term, quadratic term, cubic term. This ultimate result is x cubed minus 27, and it's still being multiplied by that x plus 2, which we had to begin with. When we factored it out, it still is in the factorization. They ask us to factor completely. Now notice when I factored by grouping, I got the same result there as I got there. So there's no real change. Whether you use synthetic division or factoring by grouping is up to you. Not everything is factorable by grouping. That's why I was saying I anticipated this problem wouldn't be. Anyway, hey guys, this is a difference of 2 cubes. This is x cubed minus 3 cubed. So we just did a difference of 2 cubes earlier. They have a sum of 2 cubes over here on this side, factored. So let's continue the factorization. This factors to x minus 3 times x squared minus or plus 3x plus 3 squared. There's still the x plus 2 that's multiplied there. X squared plus 3x plus 9 cannot factor any further. This is the complete factorization of number 22. Okay, let's move forward to section 3.5. On 3.5, we are solving polynomial equations. This gets a little bit deeper. A couple things involved, including a lot of synthetic division, still a lot of factoring. The thing is, they're not always going to give you something that can factor by grouping, and they're not always going to give you a factor to test. You're going to have to figure out which factor to use. So you have to find some. The rational root theorem states that your possible rational roots that can go into this are any factors of this number divided by factors of this number. The number I'm circling is the invisible 1. So what are factors of 12? 1, 2, 3, 4, 6, and 12. Factors of 1 are just 1. When you divide 1, 2, 3, 4, 6 by 12, you get 1, 2, 3, 4, 6, and 12. But you also have to consider the negative versions. There are a lot of reasons for that, just plus or minus these things. That's why there's spacing in between. Not for me to write in, because they're in the textbook, and plus or minus does not show up on the digital files of these for whatever reason. These are the numbers you test. What is our test with them? You have one of two options. Plug in those numbers and see until you get 0. I can plug in 1. 1 plus 1 minus 8 minus 12. Is that 0? Unfortunately, it's not. So you try the next one. Plug in negative 1. And you keep going until you get a 0. When you get a 0, you can use synthetic division on it. The alternative is to use synthetic division until you get a 0 remainder. Now, apparently, they don't show you 1 and negative 1, which I was telling you probably doesn't work. You plug in 2 or you use synthetic division on 2, that also doesn't work. You plug in negative 2, you do get 0 on it, that means that does work. Now, when you use synthetic division, remember you're also left with a smaller polynomial on top of your factored polynomial. If negative 2 is the root, then x plus 2 is its factor. So this factors into x plus 2 times x squared plus x, or minus x minus 6. And you continue solving by factoring this down or solving using any means necessary, completing the square, quadratic formula, synthetic division again, if you'd like to. Ultimately, this factors into x plus 2 times x minus 3, and your two results are negative 2 from either of these. That's called a multiplicity of 2. We'll get into that deeper. Negative 2 and positive 3. Now, I generally do not use synthetic division until I find it. I actually will plug numbers in until I get 0. Remember, either works, either the remainder of 0 or the result of 0. The reason why I do this one first is because I generally use the graphing calculator. It's also quicker for me. If I got to plug in a bunch of these on synthetic, it's going to take a while. They showed 2 tests. We probably would have done 4. You probably would have used 1 and -1 as well. That's a lot of work. Anyway, so that's part A, finding all the real solutions, solving that thing, because we couldn't factor generally. And that's the goal, right? You want a factor to use zero product property. Create a product out of it, set these equal to 0 separately, and solve from that. And factoring does that. Factoring does that, but we didn't know a factor yet, so we had to test which rational roots could exist in this thing. Notice that 3 was also one of them. Plus or minus 4, 6, and 12 weren't. Plus or minus 1 wasn't. These were possible ones, and we found our set. All right, that's part A, or that's example A. Example B, write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and the zeros -4 and 1 plus root 2. Now, rational coefficients means you can't have any square roots in your final result, which is this guy right here. In order for that to be possible with an irrational solution such as 1 plus 2, its conjugate, 1 minus root 2, also must exist as one of your things. That's where when multiplying, rationals cancel out in the right ways, or you square them and stuff like that, where you no longer have irrationals as a result. So you need to consider 1 plus root 2 and 1 minus root 2 in your factorization. Now remember, when you have solutions or zeros or roots, whatever you call them, that are like this, the -4, you got to add that 4 over to the other side. You get x plus 4 as a factor. The 1 plus root 2, you subtract it over. The 1 minus root 2, you subtract it over. That's why they have parentheses around those groupings. You distribute the negative, and if you regroup so that this time this has parentheses, you now create a difference of 2 squares and these 2 factors here. This can be an a minus b times an a plus b, which distributes into a squared minus b squared. Root 2 squared is 2. And you expand this binomial, x minus 1 quantity squared to x squared minus 2x plus 1. 1 minus 2 is -1, and now you're left with this times that. Do as we did before. So a lot of work can be involved. I kind of write it a different way, which I think is cleaner for myself. I'll probably do that as we leave that example up. And we still get to the same answer. This is your final answer for the result. This is the polynomial that gets those 3 solutions. Okay, find all real solutions. Number 23 and 24, find all real solutions of the equation. So on number 23, we have x cubed plus 3x squared minus 10x minus 24 equals 0. My first things that I look for personally are, is there a common factor? The answer is no. Can I factor by grouping? Also by my knowledge of things, the answer is also no. So we dive into rational root theorem. Rational root theorem is choose factors of 24, call those p, factors of 1, call those q, and we divide those. Factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. Factors of 1 are just 1. So when you divide these are the possible factors that'll work out. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. That's 16 different possibilities. I ain't about to use 16 different times of synthetic division until I get it to work. I'm going to plug numbers in. And if I'll do it mentally first, and if I run out of time, patience, numbers get too big, something like that, I'll use the calculator for it. Generally, you'll run into a number early on, one of these sets, probably even one of these sets, but we'll see what happens. If I substitute 1 into here, I get 1 plus 3 minus 10 minus 24. That's not 0. If I plug in -1, I get -1 plus 3, which is 2, plus 20, which is 22, minus 24, which is -2. That's close, but that's not it. Let's try 2. 2 cubed is 8. 2 times 4 is, 2 squared is 4, times 3 is 12, so that's 20. Minus 20 minus 24 doesn't work. -2 cubed is -8. This is, again, plus 12. That's 4. Plus 20 is 24, minus 24 is 0. So -2 does work. F of -2 is indeed 0. Took just as many tests as it did in this first set that they did on synthetic division. They didn't show the first 2 tests of 1 and -1, and I think that probably saved me a little bit of time. I could have gone to the calculator, typed in the equation, and plugged those into the table and also gotten 0 this time. So what do I do from here? I use -2. The one difference is synthetic division would already, when you get the 0 remainder, you also get your other polynomial. But we're about to do that right now. It's not that long. Once you know what your number is, it's not that long. All right. Because you know you're going to land on it. Okay, so there we go. So if negative 2 is a root, that means that x plus 2 is a factor. If x plus 2 is a factor and we divide it out, your other result is x squared plus x minus 12. We're setting this equal to 0 and solving. Now I can continue factoring this one down into x plus 4 times x minus 3. Two numbers that multiply to negative 12 and add to 1 are 4 and negative 3. And now that we've created a product of three factors, we can solve using zero product property, where x either equals negative 2, negative 4, or positive 3. Remember when we stated that negative 2 was one of your roots? Well, it still exists. Apparently, these were the other two roots, which don't have to be rational in those cases, but they were. So apparently testing 3 would have given you 0. Testing negative 4 would have also given you 0. Nothing on that end, which is probably all but good news. Okay, number 24. X cubed. And by the way, we're going to mention this probably, I think, in the next section. Is that the fundamental theorem of algebra? I think so. A cubic function should have 3 solutions. That's just, I expect 3 solutions on this problem as I got on the last problem as well. This also can't factor by grouping, so we're once again going to use rational root theorem. Now, this is the same coefficients of negative 24 and 1, so we can use the exact same p over q biz that we had right here. There's no reason for me to rewrite what it is I'm testing once again on this problem. Again, 0 change on that. So we'll try 1 and negative 1 again. Is this the same problem? It's close. Anyway, so we try 1. That clearly doesn't work. 1 plus 5 minus 2 minus 24. Negative 1 is negative 1 plus 5. But no, that's not going to work. 2, 8 plus 20 is 28 minus 2 works. You get f of 2. You get 0. If you're not sure of that, we'll use synthetic division and show you that 0 remainder. But try and plug in 2, see what you get. Anyway, I use 2 on this guy. And I get this guy. All right, that 0 remainder checks out. We now have, with 2 as a root, x minus 2 is a factor. I don't know how much it cares. We care to write 2 as a factor as long as we write x equals 2 in the end, right? But anyway, 2 is a factor. And this other guy's x squared plus 7x plus 12. And this is x plus 3 times x plus 4 instead of x plus 4, or what, x plus 4 times x plus 3 instead of x plus 4 times x minus 3. So very, very close to the previous answers that we got before, right? Let's compare the two. Obviously, we needed to get numbers to multiply to negative 24 or what have you. And so very, very close. Negative 2, negative 4, 3. 2, negative 4, negative 3. I mean, very close to the same thing, but not quite. All right, numbers 25 through 27, we're going to write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1 and the given zeros. So this will be a lot like what we just saw in example, the second example, that part B. We have 1. What did I write here? This should be a 25. We have a 1 and a 2 minus root 3. If 2 minus root 3 is a root, then 2 plus root 3 is also a root. Now, I prefer another method for this thing here. I'm going to show you it. Remember, if x equals 1, then x minus 1 is a factor. And if x equals 2 plus or minus root 3, then we're going to construct the factors as one combination of a larger quadratic set in a second. I'm just going to subtract the 2 over to begin with. Plus or minus root 3 are both considered when we square this, so no solutions are lost. When we square a negative, though, it turns positive, just like the positive. If I expand x minus 2 squared, I get x squared minus 4x plus 4. Plus or minus root 3 squared is just 3. And I subtract that 3 over, I get x squared minus 4x plus 1 equals 0. Just like x minus 1 equals 0, this also equals 0, part of our zero product property biz. Bottom line is, this is the other factor, x squared minus 4x plus 1. It's the combination of the two that we would have had together in the same as the example. How these two combine to become this. These two, if you wrote in factored form, would combine to become that. Anyway, I keep expanding. X times x squared, negative 4x and 1, and negative 1 times x squared, negative 4x and 1. We get the following. Like that. And we combine like terms now. We get x cubed minus 5x squared plus 5x minus 1. There's number 25. Number 26, it's arguably easier to present it in a conventional method of just writing out the factors and going to work on it. I'll show you how and why. So our zeros this time are 2, 3, and root 5. Keep in mind if root 5 is one of them, positive root 5 that is, then negative root 5 also has to be one of them as well. Let me write the black as positive as if we already had it. So this time we'll go straight up into it. We'll write f of x equals and write their opposites. We got x minus 2, x minus 3, x minus root 5, and x plus root 5. So this is fine to go about it that way, mostly because these are two binomials and, better yet, a difference of two squares. Let's multiply out x minus 2 times x minus 3, get x squared minus 5x plus 6. This is a minus b times a plus b to get a squared minus b squared. A squared is x squared minus root 5 squared is 5. So that's a quick cleanup of that one, getting that in. Not really much faster way to do it than that, so I think that's pretty good. I'm going to multiply x squared by these 3 and negative 5 by these 3. We get minus 5x squared plus 25x minus 30. And our final result is just got this x cubed. These two combined to 1x squared and plus 25x minus 30. Still a lot of terms, and those would be the results of them. So 4 solutions, degree 4 polynomial. Kind of one of those expected things. Number 27. Number 27, we have negative 2, 5, and 3 plus root 6. Of course, this will mean with rational coefficients, we also need a 3 minus root 6. Let's go to the form that they did this time, just to kind of satisfy every little bit of it. F of x equals, we're going to have x plus 2, x minus 5. Now, we're going to subtract 3 plus root 6. And we're going to subtract 3 minus root 6. So we got a couple things we still got to do with that. Meanwhile, let's touch these up a little bit. X, and they're going to have to hang out and just wait as we do the other work. X plus 2 times x minus 5 can multiply into x squared minus 3x minus 10. Meanwhile, over here, we're distributing the negative to x minus 3 minus root 6 and x minus 3 plus root 6. Now, there's no stopping us from actually doing a whole distribution of these two things, meaning x times these, negative 3 times these, negative root 6. I think it's going to take way too long, though. So what we can do instead is, once again, like the example did, treat this as a difference of two squares. X minus 3 is identical in both of these. So is root 6, but with different signs. A minus b times a plus b. Just like this last one right here is a difference of two squares. It's just one of them is an actual quantity. But it still distributes into a squared minus b squared. So let's try that. A is like your x minus 3, so that goes into x, or a squared minus b squared. Root 6 squared is, let me first write it as root 6 squared. Root 6 squared is 6, though. So again, this first term is hanging out. It's waiting. X minus 3 quantity squared expands into x squared minus 6x plus 9. We are going to now subtract that 6 that's there. And now this becomes x squared minus 3x minus 10 times x squared minus 6x plus 3. Now we're at that stage there, and you can tell why I probably preferred that other method I was stating, where we first set, x equal 3 plus or minus root 6. You subtract the 3 over. You square both sides here. Because it's not that you're not doing the same work as before. You are. It's that you're not having to rewrite everything with it. So now this is x squared minus 6x plus 3 equals 0. And that's the one that goes into right there. So we're at that stage with, to me, less work, to me, less things that are occupied and busy. And for me, I didn't have to write all this stuff as a whole. So I like that. Now we're still not done. We still have to do this 3 by 3. And if the 3 by 3 is way too much for you to kind of write out, let's do this maybe with the box method. We still have to write things out, but not in long form and not so getting lost in where our work is. So let's try and keep our work all together in a tight-knit bunch. X squared minus 3x minus 10. X squared minus 6x plus 3. Let's change color on this because I'm getting too black blind here. It turns into purple or something. Something different. Something different. There we go. All right, so here we just multiply within each inner box. X squared times x squared goes there. X squared times negative 6x, things like that. Maybe you won't lose, your signs and stuff like that when you do it this way. It's all up to you. We still have to combine like terms in the end. That's not going to change. Okay, so we got that there. Now what's going to happen in some of these cases, and it does here, which is kind of nice in cleaning this thing up, is these are the ones that will combine right here, depending on how you write it and depending on what the degrees of the original polynomials were. Because they agreed in degrees. It works out pretty well. Anyway, so this whole thing, when I combine it, I think I can do this in my final step. F of x equals, I got an x to the fourth. I have negative 9x cubed. 11x squared, 51x, and negative 30. And that is a final result. That is the final result. Okay, let's go to number 28. You use 240 cubic inches of clay to make a sculpture shaped as a rectangular prism. So that's a volume. The volume is 240 cubic inches. We're talking about a rectangular prism. The width is 4 inches less than the length, and the height is 2 inches more than 3 times the length. Okay. What are the dimensions of the sculpture? Justify your answer. Okay. So we have, let's just call the width x. Wait, the width is 4 inches less than the length. Let's call the length x. The width is 4 inches less than the length. So whatever the length is, take 4 away from it. The height is 2 inches more than 3 times the length. 2 inches more than 3 times the length. So here are our 3 expressions we can use for our rectangular prism box thing right here. Length, width, height, that kind of stuff. So for this rectangular prism, if this is our length, this is our width, and this is our height, we need to find le volume. Well, we have le volume. You can use these and compute them to become the volume. So our equation, length times width times height, area of base times height, will be x times x minus 4 times 3x plus 2, and that equals volume of 240. They're asking us to solve for x. Well, they're asking for the dimensions. We need to solve for x in order to do that. Now, these are factored, but it's not a product that equals 0. So we can't use zero product property here. We can't say either this equals 240 or this equals. No, we got to set it equal to 0 and then refactor or whatever we have to do to solve it. Maybe even rational root theorem. I don't know what this multiplies to. Let's start by expanding out. Let's actually multiply these two first. Keep the x on the outside. We'll get 3x squared minus 12x plus 2x is minus 10x and then minus 8. Now, I'm intent on subtracting this 240 over as well in just a moment. So 3x cubed minus 10x squared minus 8x. Let's subtract the 240 over, set it equal to 0. Now we're in business to try and solve this thing. Now, this is also not factorable by grouping, so it looks like rational root theorem is in the works on this. I'm not about to write all factors of 240, not even close. I will give you the idea of what you have to do for that, though. First of all, there's no common factor. Boo hiss. We can't do anything about that. Factors of 3 on bottom are 1 and 3. Factors of 240 would include numbers like 1, 2, 3, 4, 5, 6, 8, etc. All the way until, I guess, 120 would be a factor. 240 would be a factor. Things like that. We have to test all factors of these divided by 1, these divided by 3, both pluses and minuses. This is one where, as I see that 1 and negative 1 won't work on this thing, I'm more intent on using the calculator, plugging it in until I get a number that works. And keep in mind, I actually don't care about the negative numbers. We don't want negative length, negative width, or negative height. In fact, we don't want a width that's less than 4. Now that I'm starting to think about it, our domain needs to be x. Sorry, we didn't want one that is 4. X has to be greater than 4. Even if 1, 2, or 3, listen, they can be rational roots. They can be rational roots. Even if they are rational roots, I don't need to bother testing them to waste time on them. I'd rather try one that I know will work. I need a number bigger than 4. I'm going to start with 5 and 6 and 8 and factors like that until I get one that gives me 0. Even if one of the other factors is smaller, it still won't work for our set. That's why I couldn't care to even test them. So let's go ahead and go to the graphing calculator on this one, shall we? In our graphing calculator, we are going to write out this equation, 3x cubed minus 10x squared minus 8x minus 240. And let's go and ask for certain independent values. Let's go and try 5, 6. 6 works. Otherwise, I didn't know 8, etc. might have worked as well. So 6 works, okay? As 6 is a 0 for us. We're going to, is a root. We're going to use 6 on synthetic division with these coefficients. See that 0 remainder, but better yet, get the quadratic we're going to get after this. It's possible that the quadratic will be left with irrational solutions. It's entirely possible. So we'll see what happens with this. Am I missing something there? 18. Oh, 8 times 6 is not 24. 8 times 3 is 24. Let's do that again. 18, 8, 48. 40. There we go. 240, 0. I'm like, hold on. I need a 0 remainder. Something went way wrong. All right. So this factors into, remember, x minus 6 would be one of them. X minus 6, and this is 3x squared plus 8x plus 40. Seeing the numbers as they are, it is entirely unlikely that this is not only not factorable, I'm guessing this is no real solutions to them as well. Given that 6, I'll be honest, given that we just found 6 using that, it's probably likely that 6 is just, the answer for x. But if I continued forward, and I recognize that this section did not yet introduce complex solutions, but just to get you some extra practice on it, and I don't know what lies ahead, let's go play with the discriminant of this one as, it's not the same as domain, but discriminant as b squared minus 4ac. And you can tell here clear as day that with a negative discriminant here of negative 480, I believe that is, or when you subtract these, I already told you I'm bad at subtraction. Now, negative 416, I believe. That you can tell that this has no real solutions. I'm not going to get into complex answers, but just to show no real solutions there, there's no number other than 6 that works. That's what I was saying. It's worth just testing numbers within our domain to begin with, because it's likely those are the ones we need to play with anyway. So, looks like x equals 6. If x equals 6, we need to get the dimensions out, right? The length was x, so 6 inches. And then 6 minus 4, and 3 times 6 plus 2. So the length is 6 inches. The width is 6 minus 4, or 2 inches. And the height is 3 times 6, 18, plus 2, which is 20 inches. To double check this, length times width times height, 6 times 2 is 12. 12 times 20 is 240. So 240 cubic inches it is, and there's our final result. I never highlighted this problem. I really apologize, but there it is. Justify your answer. Oh, I justified it. Absolutely. Okay, let's move on to section 3.6, the fundamental theorem of algebra. This is where we will hit complex solutions. We'll talk about getting those ones with I in it. They say find all zeros of this guy, right? Now, this one is also a rational root theorem case. We're going to test some things out until we find something. So factors of 27 over factors of 1 are plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 27. Using synthetic division, we find out 1 is a 0, we find out negative 3 is a 0. Normally, we do one at a time. You find out 1's a 0, you do synthetic division on that, you get another polynomial, a cubic. Then maybe if that's not factorable by grouping, you keep going. You find out negative 3 is a 0, you use synthetic division on that. So they are skipping steps and writing out what they did on synthetic division for this one and synthetic division for this one. They said using synthetic division. Now, what did they get ultimately? X minus 1 is the factor for 1 being a 0. X plus 3 is the factor for negative 3 being a 0. In synthetic division on both, they're left with an x squared plus 9 here. Now, x squared plus 9 is not factorable. It also doesn't have real solutions. You don't have to solve using quadratic formula. You can solve using square roots, subtract 9 from both sides, take the square root of both sides. You get plus or minus 3i. I is not something totally new, not even in this chapter. We learned it in IM2, but plus or minus 3i. That means that x squared plus 9 equals x plus 3i times x minus 3i. I don't think they're asking you to write the factorization. They're just asking for solutions. So these are two solutions right here, and these are two solutions right here, here. So your final solutions are 1, negative 3, negative 3i, and positive 3i. Now, There are 4 zeros in total. The fundamental theorem of algebra states that the degree of your polynomial will tell you how many solutions there will be. There should be 4. That includes possible complex solutions, will come in pairs when we have rational coefficients. That includes possible irrational solutions in conjugate pairs. That also includes multiplicities. You could have x equals 1 once, twice, 3 times. It depends on how many, but that includes multiplicities. But you should get up to 4 zeros for a quartic function. And that's what that example is showing as a whole. Okay, let's go to numbers 29 to 31. Now, these are not the same question as you just had in your example. This goes exactly right back to the previous kinds of problems we had on the things. And if you saw and or agreed that what I did before was probably faster with my work, as far as figuring out the factorization of the 1 plus or minus 2y, they must come in conjugate pairs again, to have rational coefficients, like they're stating before. Same instruction. We're going to go about what that quadratic factorization is this way. X equals 1 plus or minus 2y. Let's subtract 1 from both sides to isolate the imaginaries, and we'll square both sides. Now, as a reminder, I squared is -1. So when you get plus minus 2i squared, that becomes 4i squared. Now 4i squared, oh, this is squared by the way, 4i squared becomes -4 because it's 4 times -1. So we add 4 to both sides and we get that. So this is one of your factors here. Because of the 3, x minus 3 is one of your factors there. So we'll multiply these two together to write out our function. F of x equals x minus 3 times x squared minus 2x plus 5. This is of least degree, a cubic, as we'll have 3 solutions as well. So let's go ahead and distribute that. We get x cubed minus 2x squared plus 5x minus 3x squared plus 6x minus 15. Combine like terms, we get x cubed minus 5x squared plus 11x minus 15. Okay. A cubic with 3 solutions. Yes. Number 30. They give us 3 of the zeros, but with the 4i, we are going to need its conjugate of -4i. I can do this much more conventionally, the same way that I mentioned the other ones can work out. -1, 2, and positive 4i, and of course that -4i. So let's write these ones out within its own set. X plus 1 is a factor, x minus 2 is a factor, and x minus 4i and x plus 4i. This is again a difference of 2 squares. You could of course argue, if you know anything about this stuff here, that it actually becomes a sum of 2 squares. How come? Let's first expand these and then we'll figure out the rest. -2x plus 1x and -2. Okay, why is this a sum of 2 squares? A squared minus b squared is x squared minus 16i squared. Well, I squared is -1. -1 times -16 is positive 16. So instead of x minus 4 times x plus 4 getting you x squared minus 16, x minus 4i times x plus 4i gives you x squared plus 16. The i's are gone. No more imaginaries. We're now real the rest of the way. And need I remind us, even in IM3, imaginary numbers don't mean they're made up. I mean, all numbers are made up, but they're no less real than real numbers are, just to let you know. Anyway, you distribute these. I'm going to start with the x squared first into these 3, and then I'll multiply 16 into those 3. And then we'll combine like terms to get our final solution, plus 14x squared. Okay, like I stated, based on fundamental theorem of algebra, we have a quartic polynomial that is of least degree with these 4 solutions, 1, 2, 3, and 4. Okay, number 31. I'm going to go back to my methods here. Now we have an irrational / imaginary, totally complex number set right there. -5, -4, 1 minus I root 3. Of course, that also means 1 plus I root 3 is in the biz. So let's go this route. Let's let x equal 1 plus or minus I root 3. Subtract the 1 over. And the same thing goes for irrationals as it does for imaginaries. When we square them, we cancel them out in the way that we want them to. So squaring both, we get again x squared minus 2x plus 1 on this side. But on this side, here's the thing. Root 3 squared is 3, and I squared is -1. So 3 times -1 is -3. Didn't matter the pluses and minuses. The fact that both are counted is important for us, but squaring those turns positive. But that I squared gives us a negative. So we have a -3, and it's just a 3, not a 9. And we can add that 3 over. X squared minus 2x plus 1 equals over here. Now, let me make sure I did everything right over here as well. Okay, so this squared a 2 to get 4, right? But root 3 squared is just a 3 here. But, plus 4 now equals 0. We're adding 3 over. Okay, so there's that guy. Now, on this other one over here, as I work these ones out, right, this would be x plus 5 times x plus 4, which now expands. If I want to say the equals 0 stuff, that's fine. Go ahead. This is x squared plus 9x plus 20 equals 0. Now that we're on the same page of both of these factors, let's go ahead and put them together, join forces. Our total function here with 4 solutions will have this x squared polynomial times this x squared polynomial. We have to expand this out in a big bad way. We used box method before. Let's see what it looks like without box method. Get rid of that equals 0. Let's try it in conventional form. I'm going to multiply x squared by these 3, 9x by these 3, and 20 by these 3. That'll leave us with, well, 9 terms that some can combine. You can do this if this helps. Multiply 9x by these 3 and line them up where they would kind of go, like the x cubes can go here. And then 20 can multiply by these 3. 20 times x squared, put them with the x squareds. And then 20 times negative 2x. And 20 times 4. So we can now add kind of vertically down these lists. Now we have x to the 4th. Negative 2x cubed plus 9x cubed is 7x cubed, and so on. 4 minus 18 plus 20. And then, so like that. So that would yield those specific solutions. Now, we haven't solved any complex ones yet. I think that's what we're doing here. Actually, I don't know if we're doing that here. No, we're not. We're not even solving any. So I guess it was worthwhile in looking at what we did in solving this one, I suppose. We might have to solve some later, just not in these sections. But number 32 and 33, we're not actually solving them. We're just determining how many possible solutions there could be. And this will kind of be in a table format. I might even want to copy and paste the table format that I had from a previous set, so I might pause this video in a moment. It says determine the possible number of positive zeros, negative zeros, and imaginary zeros, or real zeros, and imaginary zeros for the function. So this is f of x equals x to the 4th minus 10x plus 8. We're going to use something called Descartes' rule of signs, which states when you're in standard form of your polynomial, which we are, find out how many times your signs change from one term to the next term in sequence. This is a positive number, that's a negative, that's a positive. So that's one change here and a second change there. There are 2 changes from the positive set. So 2 changes. That's a possible, for positives, there are 2 positive changes at most. Now, because imaginary solutions can be in play, if they exist, they will come in complex conjugate pairs. As pairs, that means if anything is not negative or comes up as negative that comes up short of your total degree set, that means that those that need to come in pairs, in 2s, must mean that there's never a possibility of one positive solution. I forget how I wrote this before. I think I wrote 2 positive solutions or something like that. I forget what I wrote, but this is for positives only. Anyway, the point is you can have 2 or you can have any increments of 2 downward from there. Subtract 2. So that means you could also have 0. So what we're going to do in a table, I guess I'll just build this one out. There are only 2 questions, so we have to do this one. So possible positives will make possible negatives. I forget how we wrote this out before. Possible imaginaries. We have to come up with this list, and then we'll come up with the total. Make sure that the total is always 4. There are 4 total solutions in our set. So the number of possible positives in this case can be 2. It could also be 0. Now, let's start talking about negatives before we move on to the rest of the set. For negatives, the way to figure this out is you take f of negative x. F of negative x. Substitute negative x into here and see what the results appears like there as far as sign changes go. When you substitute negative x into here, negative x to the positive 4th is still positive x to the 4th, but negative 10 times negative x is plus 10x, and there's a plus 8. You can see here, you never change sign. No sign changes from this thing. Positive, positive, positive That means there are 0 negative solutions as a possibility. So you can never have negative solutions from this thing. They're only positives or imaginaries. So with 2 possible positives, you can have 0 negative, which means to still have a total of 4 solutions. That means 2 of them will have to be imaginary at least. If there's 0 positive solutions and 0 negative solutions, that means all 4 of them would be imaginary like that, which still adds up to 4. So here's your list of possible positives and negatives that can come into play on this one. Okay. Now again, these have to come in pairs of 2 because these have to come in pairs of 2. You can't have 1. If you had 1 with 0, that would make 3. That's not possible to have 3 imaginaries because they must come in conjugate pairs when you have all real coefficients here. So that's not even a possibility. You can't invent that one up. And 2 is the most it can have based on sign changes. Number of sign changes dictates the number of possible turnarounds that your polynomial can have. And when they turn around, they might hit the x-axis again. That's what it's all about. All right, let me copy this table here because I'm going to use it on the next page as we go to number 33 and addressing the same kind of question. And again, we're not solving, we're just listing possibilities. So on this one, we have negative 6x to the 4th minus x cubed plus 3x squared plus 2x plus 18. Now, as you could tell, we also care about f of negative x. Now I'm going to do this a little bit faster. Raising to an even power will keep it the sign as it was. This means this will stay negative. Raising to an odd power will change its sign. That means this will turn positive. Stays the same. Changes sign. Stays the same. So let's go ahead and look at the positive sign changes. Negative, negative, positive. There's a sign change, and that's the only sign change. That means there's one positive, I don't know what I was writing, one positive solution. Now this will also go down by increments of 2. You can't have 0. You can't have you could have 0, but you can't because 1 minus 2 isn't 0. And you can't have negative solutions. So one positive solution is the only possibility. As far as negative goes, it goes from negative to positive here, positive to negative here, negative to positive here. That means there are 3 negative solutions. And you can go down by 2's from that. That means 3 minus 2 is also 1. So here's your possibility set that we have here. When I paste this up, I have to erase what I had before. So possible positives is reduced to just, well, 1. Reduced to just 1. Now keep in mind, we have to add to 4 in every instance that we have. So you can have 1 positive solution with 3 negative solutions. If you have 3 negative solutions, 1 plus 3 is already 4. That would mean 0 imaginary solutions. You can also have 1 positive solution with apparently 1 negative solution. Leaves us with a conjugate pair of 2 right there, and then we have 4 total. Those are the only possibilities that can exist in this set. We can't have any other thing conjured up and imagined. That's it. And those are our possibilities. Remember, this was a quartic, so this still needs to add to 4 with that said. Okay, that's number 3-6. Unfortunately, we didn't get to do any solving of these ones. They chose what they chose. Maybe check the chapter test or the actual section to see more of those. We did quite a few. Our section 3-7 is on transformations of polynomial functions. Now with this is all about that A, H, and K business, things like that, where we're vertically stretching, compressing, horizontally, and doing translations and reflecting and things like that. So that's not really new biz, even from the previous chapters or some IM2, we've done a lot of it. But let's see what we got from the example. It says, describe the transformation of f of x equals x cubed. That's a parent function, representing by g of x equals x minus 6, quantity cubed minus 2, then graph. Now this kind of looks like that vertex form that we know out of absolute values and quadratics, and you can achieve the same things here. It's not called vertex form from cubics though, because they don't have a vertex. They do have a center though. This center would be at the origin, and be careful because this graph axis is scaled by 2's. So over 1 up 1 applies, and over 2 up 8 applies. Over 1 down 1 and over 2 down 8 applies. As you remember, cubing negatives turns up negative. So cubic functions look like that. That's the original graph. What does the new graph do? The minus 6 and minus 2. Minus 6 inside the function means we go 6 to the right. 6 units to the right. And then 2 units down, the minus 2 on the outside of that. Those are translations. We'll do more things, I'm sure, with stretches and compressions and reflections. But those are translations, and that's the G graph. This centerpiece goes from here, 0, 0, to now 6, negative 2. And everything else follows along. If I get to graph parent functions like that, I'll probably do the same thing. I'll start from the center and just graph off that. So let's look at number 34 and 35. Describe the transformation of f represented by g, then graph. Same kind of question. So we have, once again, the parent function x cubed. And we also have g of x equals negative x cubed, quantity cubed plus 2. So the negative x on the inside, it's interesting because you can do one of two things with it. You'll obviously get the same graph no matter what you do. But based on its appearance, the negative inside has to do with horizontal reflections. And that's what this description is going to be. The graph of g is a reflection. It's a horizontal reflection. What we call that is a reflection in the y-axis from f. Now, the other thing is a translation, followed by a translation 2 units up, like that. That's what the plus 2 is on the outside of the function. Now, they're asking us to graph both. And I'm going to use... Normally I use the tall graph, so I'll go ahead and still do that here. I probably need to do it for x to the 4th as well. So this will be attached for you. I think we already did some with these earlier. So f of x equals x cubed, I'm going to do in black. I just showed it, or it's showed on the example before, but 1 cubed is 1, 2 cubed is 8. Now 3 cubed is 27. Even on this tall graph, I can't quite fit 3 cubed being 27. But negative 1 cubed is negative 1, negative 2 cubed is negative 8. It does have that snake-like appearance. As Jafar would say, let's see how snake-like I can be. Let's see how snake-like I can be. So we're going to take that one on that side, and it curves to the other side and downward. And make sure, this is me being particular as long as there are specific points here, make sure that you ain't crossing x equals positive 3 and x equals negative 3, because we didn't hit it yet. That gets hit at y equals 27 and negative 27. So there's the original function, right? Now, given that this graph has no actual stretches, let's do this. Give me 1 second. I'm going to group it. I'm going to thicken it back out. Given that this group has this function has no actual stretches in it, it only does two things. In this next graph, oh, I did not get the arrow. Hold on. Group, please. Shoot. Timeout. 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 I'm having trouble. Give me a second. Computer technology, right? All right, copy, paste. Okay, given that G is going to do the following. G is going to reflect across the y-axis, which is going to look like this. It's also going to shift 2 units up, which is going to look like 1, 2, like that. That means when I do my graph, I'd be doing, the same things. I'd technically probably start from here and then it'd go 1, 1, 2, 8, and 1, 1, 2, 8 like that and just plot them. But that is the graph of f and g. F of x, g of x. Okay, I can't often do the copy paste thing if there's a vertical stretch of some sort, so we'll see if that happens on the next one. It doesn't look like that on the next one. Number 35, so we can probably still do more of the same. Number 35. We have f of x equals x to the 4th. Another parent function to take care of. And g of x equals the opposite of x plus 9 to the 4th power. Both clearly to the 4th power. The negative on the outside, I forgot to mention something on the previous problem. On the previous problem, what I wanted to also state is if I cube negative x, I could also write it as negative x cubed. And that also means we can reflect over the x-axis. And reflecting over the x-axis gets you the same graph for a cubic as it does as reflecting over the y-axis. That's all I'll kind of state. I'm sure I did other problems like that in the past, so I'll just leave that there. I'm on number 35. All right, this negative on the outside means a reflection in the x-axis because it affects y. So it's going to take what's kind of a parabola for x to the 4th and flip it over. But the 9 on the inside, the plus 9, means horizontal translations. This actually means 9 to the left instead of 9 to the right. So that's going to be our description of these two things here. Start with the reflection. So the graph of G is a reflection in the x-axis from F, followed by a translation, 9 units left. So we got those two things going on. Let's get our graph axes that we just used, the tall one. Let's graph the parent function of x to the 4th. This is 1 to the 4th is still 1, but 2 to the 4th is now 16. This gets quite tall quite quickly. And negative 1 to the fourth is positive 1. Here you get positive 16. So like I said, it's like a quadratic in a parabolic state. It's just significantly sharper as x exceeds 1 and negative 1. When it's less than 1, negative 1, it actually kind of squares itself off a little bit more. It goes down a little bit fatter to the x-axis, to the vertex like that. So this is a decent appearance of that graph. I suppose could be better. Now this is one of those ones where we're doing two things on it that are very similar-esque to the last set. So I'm going to copy and paste this one more time just for myself and do these two transformations. First thing I'm going to do is flip this thing over. So in flipping it over, and I actually have to bring it back down to the vertex here. Here's the reflection in the x-axis. That's the first part. Okay, reflection in the x-axis. Now it's followed by a translation 9 units left. 1, 2, 3, 4, 5, 6, 7, 8, 9 over here. And that's the result of f of x and g of x from these two. That's the movement of them. Now, if you regraph this, you're finding the points, and what you're doing is I'm starting from that negative 9, 0 point, and instead of going over 1, up 1, I'm going over 1, down 1, over 2, down 16, things like that. That's what the flip over is doing. That is number 35. Okay, numbers 36 and 37, we are going to write a rule for g. That means come up with the equation based off the problem that they give us. Now, when you look at these two problems, you see that they are presented in standard form. I'm trying to see if they're factorable. The first one's kind of factorable, but we're going to leave it. So they are in standard form. That means our final result should also be written in standard form. If you look at an answer key or something, that's what we're going to expect to see. So let's go ahead and follow up on that. So we have x to the fifth plus 3x. Now for g of x, we're going to do the following. We're going to be a horizontal stretch by a factor of 4, which we got to talk about that a little bit, and a translation 3 units right and 5 units down. Okay, we're going to do one thing at a time here. Let's begin with, now this is going to be called the graph of g, but let's begin with an h of x. An h of x where we begin with the horizontal stretch factor. Horizontal stretch factor means we apply it on the inside, and anything on the inside is inverted from what we'd normally do. Instead of 4 times x, it's 1/4 times x, because we need to make x's that are 4 times as big. That means, and this is going to be no fun for any of us, this is a very mean problem. That means for this, actually this isn't an expansion, so it's okay. It's just kind of still fractiony. We're going to take 1/4 x, substitute it for x, raise it to the 5th power, times plus 3 times 1/4 x right here. And in standard form, that means that this will now look like 4 to the 5th power is 256. No, is 1024. So now we have 1 over 1024x to the 5th plus 3/4 x. So just kind of strange. I'll make sure I wrote down the problem right for to the 5th power. Yep, that's going to be it. So that's a horizontal stretch by a factor of 4. These get that much smaller as a result. Now we're going to go 3 units right and 5 units down. So for this, we'll call this now the g of x. We're going to take h of x to go 3 right inside the function, go the opposite, 5 units down, do it outside the function, keep it the same. So we're going to replace, this is where it gets a little bigger, nastier. We're going to take x minus 3 and substitute it for x, and we're going to subtract 5 on the outside of the final result of h of x's equation. So we'll take 1 over 1024, multiply it by x minus 3 raised to the 5th, plus 3/4 multiplied by x minus 3, and this is all minus 5. So the big, honker here is expanding this guy. The 5th, if you remember Pascal's triangle, the 5th row is 1, 5, I think it's 10, 5, 1, 1, 6, 1, 6, 15. Hold on. What was it? Was it 15, 15? I can't remember. Let me check because we wrote it down. I should know it. Oh, you know what? I think it is, but I think it's 2 10s. You got to have 6 terms. So it's 1, 5, 10, 10, 5, 1. So in 6 terms are like that. Sorry, I just got to write them up there to keep them in mind. So we're going to start with 1x to the 5th times negative 3 to the 0, so just x to the 5th. And here's a minus. This is where we get to expand. So minus, so 5 times x to the 4th times 3 to the 1st plus 10 times x to the 3rd times 3 squared. I'll just write that as 9. I'm going to write less steps if I can. Minus 10 times x squared times 3 cubed plus 5 times x times 3 to the 4th minus 3 to the 5th. That's 243. Now there's still this plus 3/4 x cubed, x 3/4 x minus 9/4. I'm distributing that already. And then minus 5. Okay, long problem. I'm going to clean up this inside. They said standard form. So I'm doing standard form. Well, they didn't say standard form. I said standard form. Clean up the inside. It's x to the 5th minus 15x to the 4th plus 90x cubed minus 270. At least these are kind of clean numbers. Minus 270x squared plus 405x minus 243. And plus 3/4 x goes here. Now, this is minus 9/4 minus 20/4. I want to combine like terms there in just a bit. Now I got to distribute the 1 over 1024, which means kind of working on fraction reduction. So I'm going to let my calculator help me for that. 1 over 1024 times x to the 5th is exactly that. Now I'm going to do minus 15 over 1024. So I'm going to use my calculator there and figure out what the fraction reduction of that is. So 15 over 1024 is, I guess it can't reduce as a fraction. So it's 15 over 1024 x to the 4th. Now 90 over 1 over 2/4 should be able to reduce because I was thinking 1 over 2/4 could divide by 3. Now I realize it can't. But these can at least divide by 2. So this is going to be 45 over 512 x cubed. And then minus, let's try 270. That's 135 over 512, so 3 times bigger. That makes sense. 405. This might not reduce. Let's see. 1024 is just a lot of multiples of 2, so yeah, that can't reduce. Now, given that, 405 over 1024x. Remember, there's a plus 3/4 x that needs to combine with this. 243 over 1024, I also imagine cannot reduce because those are powers of 3 over powers of 2. Yeah, that can't reduce. So 243 over 1024. There's still the plus 3/4 x. And now there's minus 29/4 over here. So now we got to find common denominators for a lot of those two. Let's copy and paste first these first 4 because those aren't going to change. Copy those and paste them right here. Okay. The last sets here, I need to turn 3/4 into something over 1024. So 1024, I think it's 256. Yeah, multiply that by 3. So I got 768. So this is 768 over 1024x. And 1024, so now common denominator 405 plus 768 is 1173. Let's see if that reduces with 1024. I'm going to guess not. 1024. Nope. So this is plus 1173 over 1024x. And then 29, I need to multiply also by 256 to get a common denominator with this negative 243 over 124. So this has become negative 7424 over 1024. And negative 7,424 minus 243 is, so I guess this was a mean problem, minus 7,181. So minus 7181 over 1024. It's mean if they require standard form, but this should be the 5th degree polynomial expansion of g of x for this particular part of this problem as we go on to, just be nice and mean. Now, we could have kept it, I suppose, in this stage. I'm just stating that when it comes to, if they write something in standard form, generally we do as well. So here's an accepted answer. Sorry if we went full bore after that to this thing because it just gets bigger. What's nice is we did get to practice a binomial expansion of something with a negative. I don't think common denominator stuff is something a lot of people tend to care about in this stage right here, but this is the other version, I believe. I hope I did all that stuff right and didn't make a mistake along the way. Otherwise, just guys, go ahead and stick with that. This still addresses what we were trying to do in order of what we did, if that makes sense. Okay, that extended the problem overlong. Let's go to number 37. Let's see if they're like, oh man, this is a lot easier. And it probably is, because this one probably doesn't have a fraction. Okay, let the graph of G be a translation 5 units up, followed by a reflection in the y-axis of the graph of f of x equals. So, x to the fourth minus 2x cubed minus 12. All right, we're going to reflect. I always write rect first. I don't know why. We're going to reflect across the y-axis, and then we're going to go 5 up. Up 5. Okay. G of x. We're going to take f of negative x. We're going to substitute a negative to reflect across the y-axis. The 5 up is unaffected from the negative x. It's on the outside. It adds afterward anyway. So we'll be good just doing these both at the same time. So we're going to substitute negative x anywhere we see an x, like that, and then right here is that plus 5. Just kind of hits on the outside. It's just going to combine with the negative 12, right? So this becomes x to the fourth plus 2x cubed minus 7. And then you're done. Now that's standard form. That's standard form. This is standard form. Man, I feel bad going like, I don't know, standard form was a big requirement of that. Again, I'm fine with the expansion and stuff. I just hope that you need to move on if you think that that's all you had to write. So I feel bad for not boxing that at the time. Okay, let's go to sections 3.8 and 3.9, the last two sections of this review. Probably of the longer reviews that we're ever going to have. This section, this is 9 sections long. There are a lot with graphs, and we're still not done. All right. In section 3.8, we're analyzing graphs of polynomial functions. This is where we got to do more of the tableless graphing. I say that given that they did a table still. We got to do more tableless graphing whenever something was factorable. I don't think they're giving us that opportunity. So we're probably going to use more of the graphing calculator. I won't use a table per se, but I'm going to use the graphing calculator to get the constructs of this graph. What we need are x-intercepts, the y-intercept. We want turning points, local maximums, local minimums. So in this particular problem, they were in factored form. So this is going to be a little bit different. When they're in factored form, they have an x-intercept of 0 right here, an x-intercept of negative 2 right here, and an x-intercept of positive 2 right here, each with multiplicities of 1. They got their x-intercept, then they estimated points of local maxes and mins. These are ones where you really got to use the graphing calculator on them. Now they talk about end behavior. This thing is x times x times x, which is x cubed, a cubic function. It's got a y-intercept of 0 when all said and done there. It's got a leading coefficient of 1, and a positive cubic will start down, finish up like that. So they know which points they're going to hit there. They also identify a local max and a local min right here. You got to use the calculator for that. It's not quite at this number 1, negative 3. It's really close to it. But you can see that it's 1.15, negative 3.08. And as this is an odd function, something which I don't know if we'll get to talk about, this is negative 1.15, positive 3.08. It's an exact reflection of that. So that's their total graph. Our examples don't exactly hit all of this perfectly, and I didn't show in the graphing calculator what it is they did to get those numbers, but I will in these problems. The difference between their problems and our problems is theirs is factored form, ours is standard form. I'm not looking to play the factor game. I'm looking to use the calculator straight up, getting the graph and going with it. So I'm going to go to the graphing calculator right now. I'm going to plug this one in. We're going to take a look at its graph and see where it turns and does all that kind of stuff. So we will do y equals negative 2x cubed minus 3x squared minus 1. Let's do a normal table here. This is actually, you might not know why I actually choose this table, but I might have to zoom out. I don't know where this thing's going to turn. Okay, I think we get to see the instances of the turn. We get to see where it crosses the x-axis, all that jazz. Now, the first things I'm going to do is I'm going to list features such as x-intercepts. We'll talk about local max and local min points, local max and local min. So x-intercepts, should I say zeros? It doesn't matter which one. X-intercepts are zeros. Where do they cross the x-axis, right? So identify the x-intercepts and the points where local maxes and mins occur. We'll talk about increases and decreases after we do the graph itself. So going back to the graphing calculator, what you're going to notice is it crosses the x-axis here. Now, what's that exact value? Let's use the 0 function on our calculator to figure that out. Hit second and trace. Go to the 0 option. Option 2 is the 0 option. Make sure you go left of your 0. And somewhere right of your 0, I can choose 0 as the right. And let's guess the in-between, and we'll round this to, I think I used 2 decimal places at the time. If I use 3, well then, oh well. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5 That shouldn't take so long to compute. There it is. Negative 1.68, we'll say. So it's negative 1.68 for the x-intercept. I wrote that like that. Okay. Let's find the local max and min of this thing here. The local max is this guy right here. A local maximum is where this thing goes from increasing to decreasing like that. So it's that point. It might be the y-intercept. It might be 0, negative 1. I don't know. We're going to figure it out. So I'm going to go to calc again. It's above trace and hit maximum. Make sure we're left of it. Plug a number right of it like 1. And we're going to find that maximum point that goes between these two, which is right here. Now, the way that this appears, this says 1.40, etc., e to the negative 6 power, and the y is negative 1. I assume that's supposed to be 0, negative 1. That thing says 0.000001. I think it's just your calculator not being able to compute something to 0 for some strange reason. So I'm going to assume that local max is at 0, negative 1. If not, we can't tell the difference on the graph anyway. The local min, or even if we couldn't anyway, the rounding to 2 decimal places is still 0 and negative 1. The local min is going to be this guy right here. So we have to choose left of it and right of it and find where that point mins out, which is right there. And that's negative 1 comma negative 2. See, again, the calculator's kind of doing some weird stuff with decimals on that, but even if it was supposed to be precisely the number they wrote, to 2 decimal places is still that set. So that's nice. The x-intercept is the only weird one. Now the end behavior is something else that I want to make note of that graph. You saw it. It was a cubic, negative leading coefficient. It's going to start up, finish down like that. That's the kind of graph we're going to have. I'm going to use the more squared off graph paper here because it has numbers. We don't need to go as tall and short. And let's go ahead and plot away. Then we'll talk about increases and decreases on this thing afterward. So x-intercept of negative 1.68, probably about right there. We got 0, negative 1 is not only the y-intercept, but also the local max, the local min's right here. Those points are crucial to our plotting, and we're going to go ahead and graph away. So it bottoms out here, curves up, tops out here, curves down, and it finishes off going downward. There's our cubic function like that. Regarding what you're seeing here, we can also note instances of increase and decrease, intervals for which it does both. It increases from this x value to this x value, the local min to local max. So it has an increase from x equals negative 1 to x equals 0. I don't know how red came up. But it increases from negative 1 to 0 on x. And it decreases everywhere else. So it decreases from negative infinity to negative 1 and from 0 to positive infinity. Remember, it's decreasing as we go to the right is basically how we're saying it. On those intervals. So it decreases on the interval when x is less than negative 1 and when x is greater than 0. So that's all the information we need, and we're done. Number 39. We'll do the same stuff, use the graphing calculator, get all the points in, stuff like that. Now this is a quartic function, so this will have a start-up, stay-up kind of thing with a positive leading coefficient, but we'll see it on the graphing calculator. X to the fourth plus 3x cubed minus x squared minus 8x plus 2 plus 2. Okay, so let's just type it in now. I'm going to, let me just copy and paste this information just so I can get that stuff written and prepared. And I'm going to erase those numbers and replace them with new numbers, of course. So get rid of those. Okay, this is the information we want. Increase and decrease will come after we graph, okay? So let's get it started. Let's go to the graphing calculator, type that in. Where's my window feature? There it is. Okay. And my graph. We got x to the fourth plus 3x cubed minus x squared minus 8x plus 2. Okay, let's look at this graph. And this one, ooh, it does some stuff above. You can kind of tell right there. It's not just this part. So I need to do a little bit more, not zoom out. I'm going to increase my window. Let's change Y to about, let's say about 10. We might be able to see everything from there. All right, there it is. So this graph has a little W-ness to it, right? It's going up to the top and doing things, but we have three turns. 1, 2, 3 turning points. 2 of them are minimums, local minima. 1's a local maximum. We have 2 x-intercepts right here and right here as well we need to take care of. Let's start with those ones. So the x-intercepts, and it's not, the y-intercept is 2, by the way, on our graph. You can see here, it shows a y-intercept of 2. So we're going to plot that point, and then just to the right of 0 on x, there is a y-intercept, there's an x-intercept. So let's find out what those are. we'll go to 0. We'll go left and right of 0, left of 1, and find that in between. It's this number, 0.25, so about a quarter. So x is 0.25, 1y is 0, and also, let's find the other one. Left and sure, right of this thing, we'll choose 3 or something, and let's make sure that where's my cursor? 2.8. Oh, it must be over here. There it is. All right, let's make sure it's close enough to it. 1.34. So my two numbers are going to be 0.25 and 1.34. These are not ordered pairs. These are x-intercept values. So when I use the same, when I use this same graph paper, what's going on? Copy, paste, please. I beg of you. Copy, paste. There it is. When I use this same kind of graph paper, we'll have 0.25, a quarter of the way over, and 1.34, 1 1/3, like that. By the way, there's a y-intercept of 2. There's a y-intercept of 2, right? Okay, let's find those local maxes and mins. The local max, there's only one of them. It's this one right here. Let's go to option 4. Let's go left of the max. Don't go too far left so that you hit a max that's above it. So I'm only going to choose -2 as my leftmost point, unless you just guess something that's close enough. And a 0. We're going to find the highest point between -2 and 0, which will be this guy right here. And that's at x equals -1.13 and y equals 7.06. So -1.13, 7.06. I'll show you this stuff later. I'm just writing it down. Now the local mins. Let's find this one and that one. We're going to get those 2 points as well. So we have to do one at a time. Left of it, right of it. And this is -2, 6 is what they're going for there. Even if it wasn't, again, that's what it is rounded. And then the last one, left of it there, sure, and right of that, at least 2. And it's this guy down here, 0.88 and -3.17. 0.88, -3.17. Okay, so here are the points we're going to plot and go to work on that. So -1.13 and 7.06, a little bit, kind of just right there-ish, right? There's not much to it there. That's a local max, keep that in mind. -2.6 is a local min right here. So it's going to come down there, bottom out, top out there, hit down here. It's going to bottom out at 0.88, -3.17, probably about there-ish. So we have our points of our graph. Remember, it is a positive quartic. It will start up, do some stuff in between, such as this. That's very curvy. Hold on. This isn't very curvy, and that is very curvy. I want to kind of get that in between. This, still very curvy. That's okay. This, it'll bottom out, and it will curve up and finish up like so. There's our quartic function. That's the idea. I maybe made it angle too much, at least by appearance. I think those dots maybe make it look like it's angles, but it's not really. No. Okay, we'll leave it like that. I want to just erase. I want to fine tune this little part. All right, that's okay. All right, so increases and decreases. It has a couple of increases right here and here. It increases between this min and max. That's between -2 and -1.13. And then it increases again after this min right here at 0.88. Now it decreases when we are less than this min of -2. And we also decrease between the max and that min. So between -1.13 and 0.88. Like that. And that's all the requested information we have for number 39. Kind of long problems there. All right, numbers 40 to 42. Determine whether the function is even, odd, or neither. Now, I hinted at what it meant to be even at the time. Symmetry across the y-axis. Plug in -x and there's no effect on the graph. We'll see what it means to be odd as well here. So an odd function, let me actually write these out before we move on because they didn't say them. So I want these to kind of be notes. You have an even function when you plug in a negative x and you get the same y value out as you did before. You get an odd function when you plug in a negative x and you get the opposite y value as you did before. So we'll see those results. Neither case is neither. So there's even versus odd. Okay, so first one, number 40, f of x equals 2x cubed plus 3x. Let's substitute negative x into here, see what the result is. The general case and understanding of this stuff is for polynomials, you raise a negative number to an odd power, numbers will change signs. It'll turn negative or whatever. So this is negative 2x cubed minus 3x. Now, if you notice, by factoring out a negative 1 from here, just the negative, you're left with 2x cubed plus 3x inside. This was the original function. So that means we're getting the opposite of our original function. By plugging in negative x, we get the opposite of f of x. That is an indicator of an odd function. That is number 40. Number 40 is odd. Number 41, and if they do this right, they'll get 1 even, 1 odd, 1 neither. Number 41, we substitute negative x into our g of x equation. And in this case, we got to take g of negative x. Now, when you raise a negative number to an even power, it turns positive, which means the sign that you had stays as it would be. This was positive before, it's going to be positive after. This is 3x squared minus 7. If you notice, this was 3x squared minus 7, so is this. It stayed the same as it was. That means you plug in a negative x, you get the same y value out as you would if by plugging in the positive x. That is an indicator of an even function. And as a reminder, an even function is symmetric across the y-axis. An odd function is symmetric across the origin. I don't have a visual of this. Actually, here's an example of an odd function. There's an example of an odd function right there, symmetric about the origin. Some positive x gives you some y, negative x gives you the opposite y. It was right there. Number 42, I'll leave right here with you. We got h of x equals x to the 6th plus 3x to the 5th. It's something that I hinted at the time, by the way, for even and odd on polynomials. If your polynomial has only even degree terms, it will be an even function. It has only odd degree terms, it will be an odd function. It has a combination of both, it will be neither. That means this is a case of neither because we have an even degree and an odd degree. That means we won't get exactly opposite or exact same y value as before. So we could have also gotten those other answers just by knowing that. That's only for polynomials we can understand that. This is x to the 6th minus 3x to the 5th. This is neither exactly the same nor exactly the opposite because not both signs changed. This is a case of neither. So we got an odd, we got an even, we got a neither. We covered our bases, and I also spoke on what you can do shorthand for questions like that. If we do those on the chapter test, I'll probably do it that way for polynomials. All right, we have 2 more questions. We have an example to cover for this last section, modeling with polynomial functions. This example says, write the cubic function whose graph is shown. They give you 3 points as x-intercepts, which is great to write in factored form. And they're going to keep it in factored form for the final answer, by the way. And they're going to find their a by plugging in the x, y of the 4th point at 0, negative 12. Negative 12 for y, 0 for x. 0 plus 3, 0 plus 1, 0 minus 2. Multiply 3, 1, and negative 2 and get negative 6. Divide both sides by negative 6 and you get a equals 2. So therefore, in factored form for this thing, your equation is f of x equals that guy. Looks like we get to do the same thing as I'm going to start up problem number 43. We get to do the same thing on this question. Write a cubic function whose graph passes through these. We got negative 4, 0, 4, 0, 0, 6, and 2, 0. Now, just like we did for quadratic solving systems of equations, a system of 3, we could do that for these ones here, but that would take a long time because we'd have to do a system of 4. System of 3 is long enough already. So it's best to use this factored form so long as we have 3 of them as x-intercepts. X plus 4, x minus 4, and x minus 2. I'm saving the 0, 6 for our x, y substitution, where 6 goes into y, 0 goes into x. 0 plus 4 is 4, 0 minus 4 is negative 4, 0 minus 2 is negative 2. Negative 4 times negative 2 is 8, times 4 is 32, so 6 equals 32a, and a equals 6 over 32, which reduces to 3 over 16. Not the most pleasant number, but it is the answer. Let's not write it as a decimal or anything else. This is fine. I'll leave it like that. This will be f of x equals 3/16 times x plus 4 times x minus 4 times x minus 2. And there's our final result on that one. So again, in a cubic function, we're just choosing the intercepts to get there. We could do the same thing for a quartic function. I mean, it goes on from whatever you're doing. It just continues. The last question that we have on number 44 looks to be a different kind of question. Use finite differences to determine the degree of the polynomial function that fits the data. Then use technology, graphing calculator or something, to find the polynomial function. Yeah, whenever they have these things here, they are, again, probably saving you time, saving you effort and hassle to be able to do this. But it looks like it's going to be some sort of exact cubic or quartic or whatever it's going to be, depends, by finite differences. We've done these before. The first differences would lend to a linear equation if these were constant. The second differences would make it quadratic if those were constant. If the third differences are constant, it's a cubic. If fourth are constant, it's a quartic. I'm almost expecting a quartic here. This is where I may make mistakes. This is where I'm going to say use a calculator. I'm stubbornly, whatever, not going to, but I may make mistakes. So be cautious. I will fix them if I mess up. I'm finding the differences between each number. I got to subtract 13 here, minus 3, and plus 19, and then plus 53, plus 99, and plus 157. Okay, hopefully I didn't make a mistake yet, because it can happen. Oh boy, it can definitely happen. Plus 10 here, plus 22 here. So by the way, first differences are not constant. It's not linear. Second differences are already not constant, barring a mistake. They're still not constant, not quadratic. But somewhere we'll find the constant. Plus 46 and plus 58. Okay, third differences. Maybe these are constant. They actually look it. Let's see. Plus 12, plus 12, plus 12, plus 12. Okay, I didn't make any mistakes. The third order is constant. That makes this a cubic function. That means we could choose 4 of these points here, solve a system of 4 and get the cubic, or, of course, we can use it in our calculator. So in our calculator, what we're going to do for this final question is, and I'm going to have to hide away from these things. I'll type them in, but we have to go to our lists, go to stat and edit, and we are going to come up with a list here. The x values are 1, 2, 3, 4, 5, 6, 7. By the way, it's important to note that your x differences need to be constant for the differences in y's to be the constant you're looking for. So I need negative 11, negative 24, negative 27, negative 8, 45, 144, and 301. Okay, what we'll do is use cubic regression in our calculator here. They just said write the function, but I might do a few more things with this. I want to show you what these points look like on a graph with zoom stat. Oh, they didn't show up. I need stat plot on. Hold on a second. Stat plot on. Let's once again go zoom stat. So we have these points here. You might argue that's a quadratic, but I'd say this is just a portion of a whole cubic function. We'll see it as a whole when we get the whole graph. So what we get to do here is we get to go to stat, calc, and cubic regression. That's what we're choosing for our list. We can hit enter as it defaults to L1 and L2, and this is what we have here. It doesn't show my R squared because I don't have diagnostic on. Let me do that one more time with diagnostic on. Give you 1 second here. Diagnostic on, same thing. Nope, not that. Same thing as before in cubic regression. Okay, this will give me my R squared of 1, which means it perfectly fits through those points of the cubic. That means that, yes, this is indeed a cubic function. Your A value is 2. I'm going to start writing this out. That means it's 2x cubed. And then it's minus 7x squared, and then minus 6x. Now it says plus 0. The d is 0. That means plus 0 as a constant. Whether you write it or not means 0 is your y-intercept, basically. I'm going to leave it out, the plus 0. That's your function. That's your answer. And then I guess at that stage we'd be done. Now, all that told, that means if, I mean, it doesn't mean anything. We're done with the problem, I believe. But if I go to y equals, I can also plug in this equation, go to vars, statistics, and under the EQ part, go to reg EQ, it's equations. Plug in the regression equation like that. Because it has some rounding issues there. But when you go and graph it, it's going to perfectly go through these points, which is cool. Now remember, this is a cubic. When I zoom this thing out, you'll see how the cubic actually works as it does. So let's get a deeper zoom out of this thing. here, and you'll see more of the cubic function take hold there. So that's the idea of it anyway. That's what we're doing, and that's all good and dandy. And that is your final answer. Let's make sure that that's all they asked us to do in the final bit. Find a difference is determined. Use it to you find polynomial. Okay, that's it. Okay, guys, that'll do it for this one. This is a great long review. Thank you so much for watching. It covered most of everything. The things I really saw it didn't cover where we didn't get to do, specifically on the fundamental theorem of algebra, we didn't get to solve for our complex polynomials with those ones, but we got to practice synthetic division beforehand, and I hope that that was good enough for you. So guys, thank you so much. Take care. I will see you in the next one.